Close enough. Going live. All right, I'm live. We're live. Live right now. No, not yet. So I just clicked the wrong thing. Okay. This is supposed to be the link. I'm going to drop this into an announcement. Then we'll just test it real quick. Lee? Whoop. Okay. And save that. Oh, I know what I want to do is just check from my control room that you can see. All right. Okay, so we're beginning our live stream. And I will put up the study guide. And I will put up, what else? What else am I going to put up? Pretty pictures. I don't know. Okay, pipeline. And my password is, no, something. Okay, just kidding. Okay. Canvas. So two things. So we're going to get the study guide, exam 2, download that, and then we'll go back. So would you like to go over the 5 questions, or did you already do it? Anybody not do it? Okay, so I'll do them after maybe chapter 8. How about that? We'll just look at it. We can talk about those questions, okay? So the preview questions. We'll look at those after we cover chapter 8. Okay, here we go. Exam 2 study guide. Click the icon. Okay. There we go. Ooh, makes it bigger. Okay, so we're going to jump down to chapter 8 and start there because we didn't quite finish that in class. And then we'll move back and do chapters 5 through 8. Okay, so we're jumping to chapter 8. We're going to finish that, and then we'll be able to jump back. Okay, so we have in chapter 8, we're talking about the giants, which are the gas giants and the ice giants. And let's see, there's a term called, it's a funny term, but stellar occultation. Does anybody know what this means? Stellar occultation. Stellar occultation. Actually, what the heck are we talking about? Well, we're talking about something where the planets pass in front of a star. The process of the planet passing in front of the star and temporarily blocking the light of the star is called an occultation event. So when the planet blocks the light of the star, it's like an eclipse, really, kind of like an eclipse. But what happened in stellar occultations is we discovered that all of the outer planets have rings. It was through stellar occultation that we discovered this. So the main body of the planet, of course, blocked the light of the star, but we discovered just before and just after that the light of the star was being blocked as well. And that wasn't by the main body, but by rings. So we knew before we even visited Jupiter, that Jupiter would in fact have a very low visibility ring around it. So one of the things that you should understand about that is, why is it so low visibility? Why are Jupiter, Uranus, and Neptune's rings so hard to see? And the answer is low albedo. They don't reflect light well. And the reason why is they're not made of material to reflect light. So the kinds of material that reflect light well are ice, right? Ice reflects light well, but these are not made of ice. So Saturn's rings are made of ice mostly, different kinds of ice, by the way. But the rings of Jupiter, Uranus, and Neptune are mostly dusty and therefore do not reflect a lot of light. They have a low albedo. But they were discovered through the process called stellar occultation. the occultation of a star. Okay. Next word, metallic hydrogen. We learned about that today. And metallic hydrogen is kind of special. In order to have metallic hydrogen, what do you need? Well, a lot of hydrogen, but you also need this. What do you need? Pressure. You need enough pressure to push it together so that it begins to act like a metal. So, in fact, Jupiter and Saturn both have enough pressure to create the metallic hydrogen inside of their body, but Uranus and Neptune do not. And we actually don't find it any other place in our solar system, right? It's not going to be found anywhere else. It's a very special form of hydrogen that conducts electricity, and it's formed under pressure. Now, there was that really beautiful picture. The layer of metallic hydrogen is found. If I just bring up the slide for this chapter, you can see the picture. The metallic hydrogen is found where? Well, deep inside of the body, outside of the core, and then below the outer layer, which is more like an atmosphere layer. And it'll be like a normal gas. Okay, so this is the picture you want to remember. Come on in, right? We want to look at that picture. You want to see that the greenish tinged area is the metallic hydrogen. So it's outside the core. The core is made of rock and metal. And then outside that core, you have the very high density, high pressure hydrogen, which has become metallic. Outside of that, you have normal hydrogen. Okay, by the way, there's helium in here too, but it just doesn't do anything. The helium does not conduct electricity. Okay, and then the outer, the white layer is just a normal kind of hydrogen gas or high density gas, right? But it's kind of normal. All right, so we call it molecular hydrogen. Does everybody understand molecular hydrogen, by the way? It's not an individual atom, it's a pair of atoms that are together. Okay, you don't really have to know that. Okay, belt and zone circulation. Which planets have it? Well, definitely Jupiter and Saturn both have it. And what does it represent? What kind of heat flow? Called convection, right? So the belts and the zones on Jupiter are really easy to see. The belts are the darker ones, the zones are the lighter ones. And we learned today also that the circulation pattern, the belts are descending gases, and the zones are the ascending, the rising gases, right? So rising and falling gases are giving that pattern. The Great Red Spot is a storm on Jupiter. We know that one. It's been around a very long time. And what feeds it, right? Why is it still here? And the answer is ultimately energy, right? There's energy being pumped into the storm to keep it going. So will it last forever? Actually, the latest news is it might be unraveling right now. So I don't know how long it'll take or if it really will, but we see little strips of it just seeming to fly away. Is that interesting or no? We don't need that. It's not going to be on the test. It's way beyond the book, right? Okay, forget that. Oblate sphere is referring to which planet in particular? Saturn, actually. Jupiter, not so much. It's just so big that it's nearly spherical, but Saturn, it's smaller and rapidly rotating. And so it takes on a squished sphere look, right? It's broader, it's wider around the middle, around the equator, and a little smaller at the poles, okay? Speaking of rotation, these are things you're supposed to memorize. We'll get back to it in a second, but you can kind of remember the two big ones, Jupiter and Saturn. Jupiter rotates in only about 10 hours. I think that's what we found, about 10 hours. And Saturn about 10 3/4, 10.7, something like that, okay? I think the book might have said 10 1/2. All right, anyway, Cassini spacecraft. We watched a little video clip today. If you haven't seen it, go on to Canvas in the links and watch the Huygens probe landing. And that story tells us about how the Cassini spacecraft went into orbit around Saturn and was there for almost 14 years, nearly 14 years. And it dropped a probe onto the largest moon of Saturn called Triton. And Triton is special because it has an atmosphere. Okay, so Triton has an atmosphere, and they discovered that it has not only an atmosphere, but it has weather. So it has lakes and rivers and mountains and clouds, rain. It's got a whole system. The mountains and the rocks are made of water ice. The rivers and the lakes are made of hydrocarbons, right? Because it's very cold there. So it's like rivers and lakes of gasoline almost, but not quite gasoline, something like that, hydrocarbon. And water ice is the mountain, okay? Enceladus is another moon of Saturn, and this is the special one that has cryovolcanoes, which are spewing water, and they're also called geysers. We'll call them geysers too. And the geysers are shooting the water so forcefully that it's leaving the moon behind and going into orbit around Saturn. I think I should be showing you guys a picture of Saturn's rings. I don't think my slides have as many good pictures. I'll show you guys a ring picture in just a minute. Speaking of rings, some of the rings have little moons around them that seem to be keeping them in, keeping the rings in good shape, right? So the shepherd moons are disturbing the rings, but at the same time keeping them from straying too far from a nice orbit. And so we've seen that. Okay, so I didn't quite get to this today, but the Roche limit is a topic that we'll cover in the morning, but might as well cover it right now, right? The idea is that if you get too close to a body, that the tidal forces can rip a body, rip something apart. So something like an asteroid or a comet is not actually held together very strongly. In fact, sometimes we call them rubble piles, right? They're held together with a weak force of gravity, but if you try, you can rip it apart. And so if they get too close to a body like Saturn, for example, the tidal forces can just pull them into little pieces, into little fragments. Maybe fragments like the ones we find in the rings, right? So that's actually the story that I want to tell you. We know that the rings of Saturn are largely made of ice. We know that the ice should sublimate away because it's being exposed to a lot of energy from Saturn. Saturn is radiating a lot of energy. And so we see them disappearing. It's not a hard thing to understand. Saturn's radiation is making them disappear. So they're not old, right? They're not as old as Saturn. I know the book says 1 billion. I don't think he's right. I think he's wrong. But anyways, maybe the dirty parts, right? The dusty, rocky parts are, but not the ice parts. The ice, which is what we see, it's got to be relatively new. And so something came too close to Saturn and went past this Roche limit. So let's go ahead and bring up some information on the Roche limit. I don't have it in the slide, so let's use Wikipedia. Roche limit. I was going to draw a picture, but I think I could do better on this if I just show you. Okay, so Roche limit. Okay, Roche limit. I mean, I should just go to the Wikipedia page. You know it's going to be good, right? Wikipedia. Where are you, Wikipedia? No? Huh. Wikipedia, there we go. All right. Okay, the Roche limit. Okay, so if you're far enough away, you can exist, but if you come too close, you see the tidal forces are starting to stretch you. And if you go within this limit, the force of gravity is not enough to hold this thing together anymore, and it actually is being ripped apart by the central body's gravity. So this is kind of an interesting idea. And so what could happen to the pieces? They could go into orbit around Saturn, for example, and make the rings. Okay, so Saturn. Okay, so I wanted to show you the distance. It's supposed to be 2.4 or 2.5? 2.4. 2.4, right? Anybody right? Oh man, I should know this really well. 2.4 radii. 2.4. Okay, 2.4. Okay. Okay. So I guess I'm going to draw a picture. If you take a planet like Saturn and you ask, where is this Roche limit? The number can be estimated to be about 2.4 times the radius of the planet. So if I have a planet like Saturn, the main body of Saturn, and I draw a line through the center, this distance is the radius of Saturn, right? So if I say that this is the location of Saturn, the Roche limit is 2.4 times the radius of the planet. So I'm going to go 1, one more, right? And then 0.4, which is just a little less than, actually is almost about where this line was, right? So that's the Roche limit. So 2.4 radii away from the planet, the tidal force of gravity is so strong that it can rip apart a rubble pile. So if you take a typical asteroid, especially or something that looks like an asteroid from the early solar system, and it's out there near Saturn, it's going to be made of a lot of ice. So you've got this thing, an asteroid type of thing, made up of a lot of pieces. And if you bring it in too close, the tidal forces rip it apart, and then it can go into orbit. So the force of gravity will naturally cause it to go into a plane, like the ring structure is, incredibly flat. And we hope in this way, actually it can replenish the rings after they go away. So right now we know the rings are going away. They will eventually disappear. But if another icy body comes close to Saturn within the Roche limit, it'll just recreate the rings. Now, could we see something similar with Jupiter, Uranus, and Neptune? Of course, right? If a body comes too close to one of those, they could end up getting visible rings, right? Now they don't. But in the future, we may be able to see them, right? Maybe it's whenever it happened. Or maybe we could do them by man-made sources. Okay, so the other thing I'd like to share with you is there's something else about the rings of Saturn that make this kind of nice, right? So if I look up Saturn's rings, try to look, how about Saturn's rings? Saturn's rings. Images, okay. And I want to look at, okay, something like this. Okay, so you can see that the rings are not the same, right? So if you notice that there's different rings, and they have names, right? They were named in order of their discovery. So the A ring was the first to be discovered, B, etc., right? And you'll notice that there are different locations relative to Saturn's body. Some of them are more visible, and some of them are less visible. Why? Why would some rings be more visible? Albedo, the answer, albedo. They're made of different things. So Saturn actually has the inner rings are dusty, which means they have a lower albedo. You can't see them very well. So when you look with a telescope, which ones do you see? You see the icy ones. They're the ones that reflect a lot of light. Now I want you to notice there's one little stray one right here that's kind of interesting, right? Called the F ring. That's the one that's being shepherded. It has two moons, one on either side of it. And that's kind of cute, right? It's kind of cute. But other than that, if you ignored the F ring, do you notice how consistently the rings are? They're all the way through here, right? What if I told you that this distance, not the F ring, but just right here, is 2.4 times the radius of Saturn? How about that, right? So the reason why these rings are much denser could be explained by the Roche limit. This distance is where the Roche limit becomes so strong. I mean, the tidal force is so strong that it rips a body apart. So in here we have nice solid rings. And where are the rings out here? Are there any rings outside the Roche limit of Saturn? Well, the F ring is one. Okay, that's outside the Roche limit, technically. But there are two little moons there that kind of stabilize it. Oh, that's kind of exceptional, something a little bit different. Do you understand? And then I hope you're not going to ignore that there's a really big ring out here. That's pretty important. And we call it the E ring. You need to know the E ring because it's special. What do you notice about it? Is it very sharp or is it kind of fuzzy? It's very fuzzy. In fact, it's not just a ring. It's much larger. It's more like a torus in shape. So who knows what's right in the middle of the E ring? Okay, the moon Enceladus. Oh, we've heard about that moon. This is the one with geysers that shoot out liquid water all the way off the moon. What happens to the little water droplets when they go into space? They freeze into solid ice. And then what? They go into orbit around Saturn. The E-ring, this fuzzy E-ring, is made by Enceladus. We know that, right? That's where they are because there's a moon there. Make droplets up into the air, they freeze, and then they go into orbit around Saturn. Isn't that cool? All right. So anyways, we know that that's happening. That's kind of a beautiful thing. So the rings are different. There's rings that are inside the Roche limit, but are all the rings inside the Roche limit? No. But the ones, most of the rings are, and we think that explanation for disintegrating material coming within the Roche limit would be a pretty good way to generate new material. But there's a couple of exceptions, a few exceptions right here that you should be aware of, okay? Other than that, that's it, okay? All right, so kind of fun. Shepherd moons, orbital resonance. Okay, so this is an interesting idea that if one of the ways that we think the rings might be reinforced is if they have periods which are connected to each other. So 1, 2, 3 times, then there's a gravitational tug each time they go around that's going to either keep them there or pull them away so that the rings become very stable. So the rings are really exceptional. They're so thin for such a large structure. Orbital resonance is the idea that the time it takes you to go around is some multiple of the innermost piece, right? So that its gravitational tug can be exerted on you. So if it's not in resonance, then it probably won't stay there. If it's in resonance, it can go into a stable pattern. Orbital resonance. Roche limit, we just talked about. Saturn E-ring, we just talked about. What's the Saturn E-ring? The ring made by Enceladus. E for Enceladus, right? It's kind of perfect. Miranda, I did not mention that one. That's actually Uranus, so maybe I should look at the slides with you, or what do you guys think? Just random? Should we just go to a picture of Miranda? What are you supposed to know? I'm not going to make you learn a lot of stuff. 1 moon for Uranus and 1 moon for Neptune. But there are some other things you're supposed to be able to know. Well, let's look at a picture. How about that? Miranda. It's pretty easy to tell something special. What's special about Miranda? Miranda, it's around the planet Uranus. Okay. And there it is. Okay. And there you go. That's a normal everyday planet, right? A moon, right? Does it look a lot like our moon, right? Looks a lot like our moon? No? Yes? No? Does it look a little different from our moon, right? You might say, that looks a little weird, right? Okay, so here's a great thing to understand. It's really a weird creature. And actually, the neat thing is, if you just ignored, if you totally covered the bottom half and you looked at the top half, does that look a little bit more like our moon? Okay, yeah, it kind of looks all cratery and yeah, it's kind of interesting. The bottom, not so much, okay? So what is Miranda? Miranda is a violent event, right? It's 2 bodies that got smashed together, but not at such a high velocity that they blow each other apart. They merged into one. And we know that. First of all, from the morphology, the structure, they're just dramatically different, right? And then number 2, when we do a spectral analysis, they're made of completely different materials. Okay, so the top and the bottom of this picture are really completely different things. That's the only cool thing about Miranda. Actually, there's probably a lot more, we just don't know it. So Miranda, we took a quick picture as we flew past it. We did some spectral imaging. It is truly 2 different bodies that got merged together. The universe is showing us what's possible, basically. Okay, it's just one possibility. So what planet does it go around? Around Uranus. Okay, so there's 1 moon that I'm asking you to learn about Uranus, Miranda. And then we have another, and then I jump to retrograde orbit and Triton. They go together. Who knows what retrograde means? Retrograde, going backwards, right? So retrograde orbit. So let me ask you, does everybody know, as you look down on the North Pole of the Earth, which way do we rotate? Right, towards the east. Which way do we go around the sun? Looking down on the same North Pole, in this direction. Which way do all the planets go around the sun? In the same direction, right? Who could give me a reason? A reason. A law. Conservation of angular momentum. That is a reason, right? The original cloud that made our solar system was swirling a little bit. And then as you collapsed it, it had to swirl faster. It had to rotate faster. Conservation of angular momentum says that. Everybody should go that way. Yeah, everybody does. Oh, not everybody. Okay. So Neptune has one moon, a big one, that's weird, right? What does that mean? It goes the wrong direction. All of Neptune's other moons go the same way, pretty much all, not all of them, okay. But this big one is going in the wrong direction. So here's a quick question. Was this moon born with Neptune? Was it born out of the same process that created Neptune? No, not possible. Conservation of angular momentum says everybody goes the same way. Therefore, how did Neptune get this moon? It was captured. We know that, right? It had to be captured. And we actually have a hypothesis that it is a captured Kuiper belt object. It's captured from the Kuiper belt. We'll learn why later when we talk a little bit about Pluto, but it has all of the characteristics that we expect a Kuiper belt object to have. And if you remember, since they're so far away from the sun, this is where you get lots of other kinds of ices, right? Not just water ice, lots of other different kinds of ices. So retrograde orbit means going the wrong direction around the sun. And Triton is kind of special. It's special. And it's the only moon of Neptune that I'm going to make you learn. So just one moon for Neptune, one moon for, I guess I better put Neptune. Neptune moon, okay. Oh, NASA, I like NASA. Oh man, I don't know what's going to happen. You know, a Wikipedia page might be better. It's pretty interesting though. It is unusual. Okay, Triton was discovered in 1846. How about that? It is the largest moon of 13. It is the only large moon that orbits in the opposite direction of its planet's rotation, a retrograde orbit. Okay, and scientists think Triton is a Kuiper belt object, right? So these are important ideas. It shares many similarities with Pluto, which is also a Kuiper belt object we'll get to. Like our own moon, Triton is locked in synchronous rotation, tidally locked. But my favorite thing about Triton is that it has, covered with ice and stuff, it has very special kinds of cryovolcanoes. Okay, very special kind. Actually, I feel like we should look for that. Let me put that on. Let me see if I can see that. Cryovolcanoes. So cryovolcano, okay, dome, cryovolcano. Enceladus, okay. We don't know exactly how they work. Where's Triton? Triton. Okay, that didn't work. How about Triton geyser? See if the geyser is working. Okay, ice geyser. You know what? Actually, I don't know what Thunderbolt is. Let me go to Wikipedia again. Okay, so this is, here we go. It has plumes of liquid nitrogen. So this time it's a little bit different. It turns out there's a lot of nitrogen ice, and the geysers on Triton, we think, are liquid nitrogen, which is kind of different, right? So nitrogen exists at an even colder temperature, and we have solid nitrogen ice, and then we have liquid nitrogen geysers from Triton. It's kind of interesting. It also does have, I can't see anything in this picture, but it has a very, very weak atmosphere, which is kind of interesting. But again, don't consider that. Titan sounds similar to Triton. Titan, the moon of Saturn, is the only one with a real substantial atmosphere. Okay, so I should go back to the study guide. Okay, so we've covered the terms on the study guide. Let's look at the be able to. Describe how the intensity of sunlight changes at greater and greater distances from the sun. And we know what this is called. This is called the 1 over distance squared, the 1 over distance squared. What's the term for that? Inverse square law. Okay, there we go. And so the further away you go from the sun, the weaker the sunlight is. We know Earth is 1 AU from the sun. So if you go 2 AUs, what happens to the sunlight? It's 1/4 as bright. If you go 3 AUs, it's 1 1/9 as bright. If you go to Jupiter, which is 5 AUs, it's 1/25 as bright. And Saturn, 10 AUs, 1/10², 1/100 times as bright. Okay, so the further away you go, the weaker the sunlight is going to be. The intensity goes down. How is Io the most volcanic body in the solar system? Volcanism implies a lot of heat energy. Does Io have a lot of heat energy from when it was formed? And you would have to say, no, that can't be it, because it's small, right? As small as our moon, even smaller, I think, a little bit smaller. And therefore, where is it getting its energy from? It is being pumped in by being next door to the biggest planet in the solar system, Jupiter. So what's the process called that leads Io to become volcanic? We call it tidal heating, right? Or tidal forces. It's tidal friction, it's tidal heating, tidal forces from Jupiter, right? You're right next to, it's the innermost moon, the largest planet in the solar system. So the tidal forces are extreme. Okay, why is the ring structure of Saturn so special? And the key thing I mentioned today is that it's huge, right? How much? 340,000 kilometers. I think that's what it is. 340,000 kilometers. It would just about fit between the Earth and the moon, okay? The rings, but only 10 meters thick. That's the width of this room right here, right? That's pretty amazing. But they're also amazing to look at too. So if you get a chance, Saturn will be up a little bit later in the evening, but at the star party in July, you should be able to see Jupiter and Saturn at the same time. I mean, the same night. Okay, why are Saturn's rings so visible but not the other giants? We already mentioned this. What's the answer? One word? Albedo. That would be a one-word answer. Or what are the rings of Saturn that are most visible made of? Made of ice, right? Which reflects the light really well. Some of the other rings of Saturn are not as visible because they are made of dust and rock, right? And so they don't have a high albedo, they have a low albedo. They don't reflect the light well. Why is Titan such a special moon? Okay, again, there's so many things about it, but what's the number one thing you think about? Atmosphere. So it has weather, right? It has a climate. It has a whole cycle. It's not the water cycle. You probably learned about the water cycle when you were a kid. The way that water evaporates, turns into clouds, rain comes down on top of the mountains, wears them away. You have streams that flow into lakes and rivers and so on. All of that is true on Titan, but not with the materials that we have on Earth. So instead of silicates for rocks, what are the rocks on Titan? Water, ice, right? Instead of water flowing, liquid water, what do we have as our liquid on Titan? Hydrocarbons. So methane, ethane, butane, they are the liquid. But otherwise, it's very similar. It's got mountains, lakes, rivers, deltas. It's got winding rivers, lakes, and they have summer and winter and all that cool stuff. Anyway, okay. Why is Uranus? Ooh, I didn't talk about this. Who knows why Uranus has the most extreme seasons? Maybe I should look at the slides. Shall we look at the slides, or you guys understand it? Okay, it has a tilt. It's like 98-degree tilt. It's like right on its side. So that means instead of a 23.5 degrees, it's on its side. One side of the planet is getting a lot of sunlight compared to the other side. The other side gets almost nothing, right? So this is the most extreme tilt, right? Uranus takes 84 years to go once around the sun, right? 84 years. And how much of that time would be spring? About 1/4 of it, right? A quarter of the time, about 21 years, you got spring, 21 years of summer, 21 years of fall, 21 years of winter, right? Same as we do. But one side of Uranus is always going to get more sun than the other side, right? Dramatically different. Make sense? Yeah. Why is it tilted? Why are we tilted? That's probably the same answer. Why? An interaction with another body, right? Something happened. If nothing ever happened, you'd be like this. You would stand up straight forever, right? But if something hits you, then there's a possibility through that interaction to change your angular momentum. It's all about angular momentum, right? So if you had to get hit, something hit it. How, why, I don't know. But something happened. Again, it's just story, right? I don't know the exact details there. There's got to be something like that. Okay, describe the peculiarity of the ice. Oh, I know, I forgot something. Oh, it's not on here? Oh, man. I don't think I put it on here. Does anybody remember why Uranus and Neptune are so blue? It's actually kind of an interesting story. Yeah. Okay, so the methane in the outer atmosphere of the ice giants absorbs red light preferentially and reflects blue, so they look blue. Yeah, it's kind of a fun thing. So why don't Jupiter and Saturn look blue? Because they don't have that same stuff. They're mostly hydrogen and helium. So because they don't have as much hydrogen and helium, Uranus and Neptune display this beautiful blue color. And they both do look really blue if you see them with a telescope. It's kind of fun. All right, so I didn't ask that question. But what's peculiar about the ice giants' magnetic fields? What would be the one thing that you want to remember? They are aligned with the rotation axis or not. Which one was it? What's peculiar? So when you do the dynamo effect, it kind of makes sense that the magnetic axis lines up with the rotational axis. That makes sense. When you have the ice giants, it doesn't seem to work. So that means that it's not a simple dynamo effect. There's something else going on. Obviously, it is the dynamo effect, but not with a bulk material in the core like we have with the Earth and all the other bodies that we can explain. So these ones are a little bit strange. So there is a mechanism for electricity flowing, but it's a little peculiar, right? It's not a bulk effect. It's not a major component. It's something like at the edges of the mantle for these planets. We think something is happening there. Okay, so it's a little bit strange. So the anomaly is that it's not lined up with the axis. It's at an angle, a great angle to the axis of rotation. Whereas Jupiter and Saturn are really well aligned, and the Earth is pretty good too, right? I mean, those are the ones that we can say kind of work really well. Describe what is so unusual about Triton. What's unusual? Big thing? We read it on the NASA site. The only big moon going in the opposite direction, retrograde orbit to its planet, the only one. And where did it probably come from? The Kuiper Belt. And the reason why, you'll learn, right, it really looks like a Kuiper Belt object. It has all of those different kinds of ices in it, not just water ice. And we know that those are very common out in the Kuiper Belt. Compare and contrast the layers inside the giant worlds. So what do they all have at the center? They do or they do not have a, what's the center? A core. Do they have a rocky metal core? Sure, they do. But what's the big difference between the gas giants and the ice giants? The amount of hydrogen and helium, which also leads to the amount of mass, which leads to the amount of pressure. So only Saturn and Jupiter have the metallic hydrogen, and the ice giants have much more ices, and they actually have a circulation like the Earth does, a mantle where ices are circulating, and that convection is how they move heat from their inside to the outside. Okay, that's kind of the big thing. Oh, how about sizes, right? How big is Jupiter? I said it already a couple times with you guys, but just trying to remember. How big? 11 times the size of the Earth, right? How big is Saturn's body? 9 times the size of the Earth. Uranus and Neptune? 4 times the size of the Earth. So you could actually make numbers out of this. What's the size of the Earth? Some number. How about the diameter of the Earth? 8,000 miles. Okay, let's try that. 8,000. What's 11 times 8? 88,000, right? Jupiter is 88,000 miles across. Saturn, 8 times 9? 72,000 miles across. 4 times 8? 32,000 miles across. So they're pretty big. They are big. They're really big. But that gives you an idea. Okay, name, memorize. Okay, memorize the 4 Galilean moons. These are in order. The one that's closest is Io. Europa's next. Callisto, Ganymede. Rotation and relative sizes. I just did that with you. Rotation rates. Anybody remember the numbers? So about 10 hours for Jupiter. 10.7. Could almost call that 11, huh? 10 and a half to 11. I don't know. Something like that. It's a multiple choice test. So come up with the closest answer. We saw 10.7. 10 and a half, I think I asked you on one of the Phil quizzes. How about Uranus? Anybody remember the number? You just wrote it down today. Help me out. 14? Oh, 17 and 17 for Uranus? Okay, so 16 and 17? Okay, 16 and 17. Okay, something like that. So 16 hours. So we got 10, 10.7, or call it 11 hours. 16 and 17 or 17 and 16? Which one was it? 16, 17. Okay, all right. Okay, orbital periods. How long do they take to go once around? Anybody remember? So let's see. Jupiter, how long does it take to go once around? Almost 12 years, 11 years. More. You say 11 or 12, that'd be okay. It's actually close to 12. Saturn, how long? Somebody told me today, 29.4, so like 30 years. Okay, how about Uranus? We just mentioned it a few minutes ago. 84 years. And Neptune, we didn't talk about that one. How long does it take? A long time. How much? 185? 165. 165 years. Whoa, 165 years. So how many times has Neptune gone around? How many Neptune years are you old? 0. I'm 0 right now, right? If I count in Jupiter years, I'm only 4 Jupiter years old. Yeah, there you go. That's whatever. Yeah. Okay. Okay, so that's 8. All right, so let's just take a second and do those preview questions just for fun. Preview questions, okay? How many people have already done this? Ooh, half of you, okay? So the other half of you, I'm kind of spoiling it, but I want to talk about the ideas. Hopefully you'll remember those, okay? So we believe that all people are good inside. And what happens is never mind, okay. We believe that all the terrestrial planets had primary atmospheres made of carbon dioxide. And why would that be? Why would they be carbon dioxide? Where does that come from? Anybody remember? Carbon dioxide is one of the gases that escapes when you have volcanic activity. Okay, so everybody had volcanic activity in the beginning, at least, for sure. Right? So everybody has volcanic activity, everybody has carbon dioxide. And then only the Earth shows a secondary atmosphere of nitrogen and oxygen. Why? Because of life, right? It's life that made that possible. What happened to most of the carbon dioxide that was once in the Earth's atmosphere? And number one, it was transformed from radioactive decay. No, that would be weird. I mean, it could be, but it's not. It is still here, but locked into Earth's rocky material. Is that true? Actually, that's the right answer, but why? Because life put the carbon dioxide into its body and then died. And as it died, it was buried under layer after layer after layer. It became rock. So the rocks incorporated the carbon dioxide that was once in living things. So that's the reason why the rocky material was once alive stuff, right? That's an amazing thing to think about. It was blown away by the solar wind. No. It was captured by volcanoes. No. It comes out of volcanoes, and none of the above are correct. Okay, so you got the right answer. Everybody understand? Okay. Number 1. Number 2. The origin of Mars moons, okay? What are the possible answers? The origins of Mars moons. They could be captured. They are currently, so they look like asteroids. That is true. That is a fact. They look like asteroids. But it is also a fact that they have what kind of an orbit? A circular orbit. And so when you hear capture, do you think circular orbit? No, you think highly eccentric, elliptical orbit, right? So circular orbit doesn't go with capture. They don't work together. All right, so which one is right? It is currently an area of active investigation. It is a captured asteroid. It was ejecta from giant impacts. By the way, both of those are possible. They're fragments of a larger body. I'm not sure how that worked, but maybe fragments of Mars, but other than maybe, I don't know. But the idea is there's 2 possibilities really. It could be captured, or it could be like the moon formation. A collision happened and the material sprayed out, went into orbit, and then became these things that look like asteroids. Okay, which one's right? We're not sure. Okay, how do we find out? We go there, we test it, we get the samples and we test them. So the right answer is currently an area of active investigation. Okay, and so we won't know for a while, probably. Number 3, the asteroid belt. Where is the asteroid belt found, by the way? Between Mars and Jupiter. Is it completely filled up? Not quite, right? There's a gap between the edge of the asteroid belt and Jupiter, a pretty significant gap, because Jupiter disturbs anything that gets in its neighborhood, right? And that's what it did. But it didn't quite get to that area that's further away from it. So it stayed. How long has it been there? For a long time, right? A long time, since the beginning of the solar system. So it is the debris field of a destroyed planet. Some people who haven't taken astronomy class think that, right? You don't think that. Because if you put it all together, would you get something very big or very small? All of the mass in the asteroid belt is not even enough to make a moon, okay? Not even our moon. So it was kept from forming a planet by the gravitational disturbance of Jupiter. Does that sound reasonable? Maybe, okay. Consists of roughly spherical bodies made of silicon and iron. Not sure where you're getting that. That would be kind of weird. That would be aliens, right? If it was a bunch of spherical bodies, you would think aliens did it, okay? I mean, really, why would that be? And contains as much mass as Saturn, not even close, okay? So the best answer would be, was kept from forming a planet by the gravitational disturbance of Jupiter. Although it's almost like it wasn't disturbed by Jupiter. I don't know if that's a great answer, but that's what it is, and it's on the test just like that. So the right answer is, was kept from forming a planet by the gravitational disturbance of Jupiter. Now that I listen to that question, I don't like it that much anymore. But it's on the test anyway, so whatever. Earth's magnetic field is created by interactions with the solar wind, electric currents in the outer core, the magnetized inner core, iron deposits in the crust, and the right answer is the dynamo effect, right. The outer core, which is not solid, is made of molten metal, can conduct electricity. So the outer core is where the magnetic field is being generated by the dynamo effect. So electric currents in the outer core, right? So there's the inner core, which is solid. The outer core, which is molten, can move. Then you got magma, with a mantle, upper part of the mantle, and the crust is called the lithosphere, right? Lithosphere. I won't mess that up. And the fifth one, ooh, look at this. We just talked about it. Neptune's moon Triton is unique among the large moons because it is geologically active. It is, but it's not unique, right? There are other bodies that are geologic, like Io, like Enceladus, like Europa even, right? I didn't mention that, but okay, there's other geologically active bodies. Has a retrograde orbit, is that true? That is also true, okay. Has a high albedo. I don't know. Actually, if you look it up, the answer is it doesn't. Oh, it's not unique, by the way. That's not unique. Sorry, that's what it is. It does. It's made of ice. Okay. It's pretty high albedo. Has an atmosphere. And that is not unique either. So the only unique thing is the retrograde orbit. Okay. Okay. All right. There you go. Okay. So let's jump back to chapter 5, or do you want to go to 7? Why don't you take a quick vote? How many people want to go 7? How many people go 5? Back to 5. Okay. So 7 wins, but not by a huge amount. So we'll just work backwards. Is that okay with you guys? We'll still cover the material. We'll just work backwards. Okay. Chapter 7. Anybody know how to do this? There we go. Max savvy. I'm not max savvy. Okay. Okay, Mercury, Venus, and Mars. What are they known as? Terrestrial planets, right? Okay, so here's a word. Differentiation. What does that word refer to? Differentiation. Yeah. Okay, so when you have a molten body, right, it's got to be hot and molten. It can separate into layers by density. And the innermost one is the highest density, and the outermost one is the lowest density. This is how we think all the terrestrial planets formed their metal cores, rocky mantles, and crust, okay? So differentiation, the process of separating by density. It requires you to be molten, okay? That's a requirement. If you don't get to be molten, you don't get to separate. Okay, number 2, cooling. What does that mean? Take a hot body and let it sit there in space. Does it have any way of getting colder? Is there any way for a body sitting in space to get colder? Only one. What is it? Radiation. That's the only way. but it works. It works really well. And so after you cool, which part of you becomes solid first? And the answer is the outside. You get a crust. Cooling means you get a crust. So a crust forms on the outermost part of the body, whether it's a moon or a planet, doesn't matter. These are solid. These are made of mostly metal and rock, right? Not the gas giants. They won't do that. Second, third step. This is the 5 steps in terrestrial planet formation, right? Third step is called cratering. What happens after you form a crust is stuff starts to hit you, right? So when you have impact events, you create craters all over the body. And by the way, we look at the moon, right? And parts of the moon are very old and parts of it are not as old. The way we know is by the number of craters. So when we have lots of craters, we say that's an old surface, and not so many craters, we can say it's pretty young. Okay, so cratering is the process of something getting hit by debris left over after the formation of the body and after it's cool. Magma flooding, if you have some really energetic cratering or big objects colliding, then they can crack the crust and allow magma to come up and fill up any holes in the ground. Any valleys that you have where you cracked it are going to fill up with basaltic material, lava type of material, magma. And so they won't be valleys anymore. They'll be flat. There'll be ponds of molten rock that solidify into plains of basaltic rock, right? And then finally you get weathering, but not for everybody. In order to have weathering, you need an atmosphere. You need an atmosphere, okay? So do most moons have atmospheres? In fact, almost none, really. There's very, very few, but we do know one important one, and the name of that one important one is Titan. Now, Triton does have a little weak atmosphere, but I almost prefer that we just forget it. Just talk about Titan. Titan's the most significant atmosphere for a moon. Actually, I really want to tell you why, though. Does anybody have a reason why Titan would be able to have an atmosphere, but everybody else, every other moon does not? Like, what's special about Titan? It's big, okay. Why does being big help? Stronger gravity, right? It's got stronger gravity. Why'd you say that? Huh?
Differentiation.
Oh, differentiation. Okay, that's true. The moons probably do that. The moons do differentiate. We already know that our moon did, but our moon doesn't have an atmosphere. Why not? So number one, you've got to be pretty big. Like our moon would be big enough, actually. Our moon should have an atmosphere, right? Well, there's another problem, right? The gases actually, without any protection, remember Mars lost its atmosphere. What was protecting Martian atmosphere before it got blown away? The magnetic field, right? So it helps if you have a magnetic field. If you're too small, you cool off, you're not going to have a magnetic field, then you're going to have a hard time. But it turns out that there's a great benefit for Titan because it's located so far away from the sun. The solar wind is much weaker out there, isn't it? Right? And the intensity of sunlight is much weaker. In fact, the temperature is much cooler. So Titan is a big enough body, but also happens to have the right conditions where it's cold enough that the gas molecules don't escape. So in fact, if somebody asks you, why does Titan have an atmosphere? The answer is, it's pretty big and it's really cold, right? And that's how water ice acts like a rock on this planet, like a mountain, and how the liquids are the hydrocarbon materials. It requires a very low temperature. Okay, so anyway, it's not really, I don't know if it's on your test, it's just interesting. I think it's cool. Okay, weathering, Wrinkle Ridge. Anybody know what planet we're thinking about? Wrinkle Ridge. The technical term is a lobate scarp. What planet are we talking about? Mercury or our moon. They both show evidence of that. In fact, somebody in the lab last night saw this ridge, and that actually was a lobate scarp. That's kind of cool. When they look through a telescope. So anyways, a wrinkle ridge is the idea that the skin, the crust forms, and then what? What happens next? As it continues to cool, the core shrinks, right? Because it's cooling. And now the skin that formed originally for a larger sized planet doesn't fit anymore. And so it has to fold. And so the wrinkle ridge is a cliff formation that can occur when the crust folds itself. And so we also call it a lobate scarp. So wrinkle ridge, a fold in the crust that occurs as the planet shrinks. And the reason I want to bring this up again is because NASA announced a couple years ago that even though it's incredibly dead, Mercury is still forming new wrinkle ridges. So what does that mean? Mercury is still cooling off. It's still shrinking. So if I tell you a planet is dead when it stops changing, is Mercury still changing? Well, it's still changing, even if it's a tiny little bit. Okay. So it's kind of a trick question. You have to be my student to get this right because your textbook won't talk about it. But anyways, this is something that you should understand. We call it dead if it doesn't change. If it does change, it's alive, right? If the surface features change. Fossil magnetism, just an idea, quick little idea, right? Fossil, you know what a fossil is dead, right? It's a remnant left over. Fossil magnetism is a remnant of the original magnetic field. There are materials that can become magnetic. And so if they have a lot of iron in them, for example, they have the ability to become magnets. And if they're in the crust or other parts of the body, and they were originally magnetized, they can keep that. And so we can actually detect that. Mercury has it, Mars has some of that. But it's not coming from the dynamo effect. It's coming from solid material that happened to be lined up with the original magnetic field. Don't worry too much about that, okay? All right, tidal synchronization. This would be, what are we thinking about? Anybody? Our moon would be a great example. And we call it synchronous orbit. What's happening? The period for rotation matches the period of revolution, right? Synchronized. And why did this happen? What force made this happen? Gravity, but specifically, is it just the force of gravity or the difference in the forces of gravity, right? Right. Outer, inner. So what do we call that? The difference in gravity is called the tidal force, right? That's what it's really all about. So the tidal force, the difference in the force of gravity between the near and the far side, eventually slows things down and makes it so that one face will always face the central body. So we see this with our moon. Our moon is tidally locked. How about Mercury? Is Mercury tidally locked to the sun? And the answer is not yet. No, not quite yet. And how do we know that? Well, Mercury rotates one time in 59 days, 55 days, 50 and 59. Which one is it? 50. Hold on, I figured it out. 59. Okay, 59 days. And it goes once around the sun in about 88 days, maybe a little less. Okay. And they're not the same number, right? As a result of that, it's not tidally locked yet. One day it will be. Okay. But right now, not yet. So it has an orbital resonance. That word is right there. And so what that means is that the rotation happens 3 times for every revolution. So it's a 3-to-2 rotation, revolution, resonance. That's what we call it. Okay. So it rotates 3 times every time it goes 2 times around the sun. That's a resonance. Retrograde rotation. Anybody know what we're talking about? Which body? Talking about Venus, right? And another way to say it, instead of saying that it's rotating backwards, what's another way to say it? It got flipped upside down and is rotating the right direction. So in other words, Venus is really messed up, okay? It's either rotating backwards or it's rotating the right way but got flipped upside down and it looks like it's rotating backwards, okay? Either way, it's pretty messed up. What would have caused that? Somebody asked the question before. Why is Uranus on its side? Why is Venus upside down? The answer? An event. A collision type of event, right? Knocked it off its regular, its beautiful vertical axis, and now it's upside down. Okay, so that was an extreme one. Caldera, ooh, actually I meant to tell you this word. I described it, but I forgot to tell you the word. Okay, when you look at a volcano, an erupting volcano, the lava can spill out the side and make a new layer, and if it keeps doing that, you get something called a shield volcano. That's a typical volcano that you might have heard about, Hawaiian volcanoes. They've actually been all over the world, right? We have them in California even, shield volcanoes. But if you have a volcano where the lava is pushing up and then doesn't quite emerge and then gradually subsides, then you'll see that in the middle of the volcano you have a depression. Okay, so in fact, it's any place where you had a push of magma and then the magma flows back away from that position. And now instead of being a bulge, it's a depression in the ground, a caldera. That's the name for it. So does anybody want to guess what planet I'm referring to? The word corona is right underneath it, and it's the same planet. And I actually tried to describe how the coronas form, coronae form on this planet. Who knows the name of the planet? The planet is Venus. Venus is the planet, okay? So on Venus, we don't see any active volcanoes, but we see these funny little pancakes of lava flows that are 15 to 20 miles across, and they have little depressions in the middle of them. But they weren't always depressions. They were originally little hills, and the lava leaked out and went in every direction because it's very flat. And then the lava receded, or the mantle receded, and now it turned into a caldera. That's the word for it, okay? Caldera would be, it looks like a crater, but it's not a crater. It's the receding magma makes the ground sink a little bit there, okay? All right, retrograde, caldera, corona. Corona, you guys know what I mean? Let's see if we can find some corona pictures. This is not the beer. I know you want the beer. Corona. Corona, coronae, okay? So do you see the pancakes, right? I like pancakes. You guys like pancakes? Saturday morning, right here. Do you see the pancakes? Look at how circular they are. How does that work, right? Why are they circular? Because they came from a common point, and the land is very flat. They spread evenly in all directions, right? You get a circle. That's naturally what you get. And so they occurred, and in the middle of each one, what do you find? A caldera, right? The caldera is the remnant of the little bulge that then opened and spewed out some flow, some magma flow. And then the magma receded and it went down. So each one of those is an example of a corona, each one of these. So together they're called coronae, okay, coronae. So they're not like the Earth volcanoes. They're much more mild, right? They're just kind of an oozing across the surface. Okay, Olympus Mons. What is that? Olympus Mons. The largest volcano in the solar system, but on what planet? Mars, okay? It's found on Mars, the largest volcano in the solar system. And again, it's cool that you know that. You're supposed to know that. But what is special about it? It actually tells us some interesting thing. Where do the volcanoes form on Earth? Where the crust is a little bit thinner and the magma can come up through that crust, right? Now, on Mars, we don't see any evidence of plate tectonics. There's no mountain ranges. There's no spreading center. There's no continental collision. All those things that we're going to talk about in a few minutes, right? Continental collisions, subductions, transform faults. What else? Hotspots. We're going to have hotspots. That's the only one, right? I feel like I missed one. There's 5. Which one? Spreading center. Okay, spreading center. Right. Thank you. Thank you. Okay. So Mars shows this volcano that grew and huge, right? So what does it mean? The hotspot did or did not move? Or did the plate move or not? Sorry, the plate did not move, right? The plate stayed in one place. It just kept growing and growing and growing. And I also mentioned that if you took that same volcano and stuck it on the surface of the Earth, what would happen? It would push the crust down and it would not be able to exist. Our crust is just not strong enough. So immediately when you see a structure like that on Mars, what does it tell you? Even if you don't measure it, what can you infer about the thickness of the crust? It's much thicker, much stronger, right? It can hold up such an incredibly large, that's huge. Actually, we don't talk math in this class. But remember, this is a volcano the size of the state of Arizona, okay? I don't want to get into math, but I do want to. I kind of want to tell you something, right? If you double the size of one dimension of something, what happens to the mass? It gets not 4, it goes as the dimension cubed, which means it's 8 times the mass. So if you remember, how tall is this volcano? It is like almost 3 times as large as the tallest mountain on Earth, right? Which means it has 3 times 3 times 3, 27 times the mass. This is huge. Okay, it couldn't exist on our crust. The crust is not strong enough. All right, something else that we have learned about the crust: Mars has one single plate that covers the entire body. Okay, it doesn't have any plates that move around. Okay, does it have any quakes at all? By the way, we're finding out now. The mission called InSight landed a few months ago, and it's right now trying to record Mars quakes. Okay, so we'll find out by next year. I'll be making the students learn, oh yes, Mars has quakes, and, right, we'll know a little bit about, maybe, we'll see. It might take a few years. All right, Valles Marineris, I spelled it right here. What does it mean? What is it? The Mariner Valley, right? It's a big, long Grand Canyon on Mars, right? It's huge. I think we read 2,500 miles long. I thought it was about 100 miles wide, maybe 7 miles deep. It's an incredible canyon. Jumping forward, blueberries. How do you spell blueberries? Or do you put an E on there? Blueberries. I'm pretty sure it's blue, right? That's a spelling mistake. Anyways, they're not really berries at all. They're the mineral called hematite, which is an iron oxide material. But the interesting thing is they can only form in liquid water. So we know that if they're on the surface of Mars, liquid water was once at the surface of Mars. We found them very early on, and so you need to know that. Okay, Noachian period, Hesperian period, Amazonian. See, I left out pre-Noachian. I wonder why. Where is the pre-Noachian period? Well, just before Noachian, right? I guess you can figure that out, right? Hesperian period would be after the Noachian, and Amazonian is the period today, right? But actually, the most important one you need to know is the one when life could have existed, which is which one? The Noachian, right? That's the period where life was good on Mars. What was good about the life on Mars? Tell me what was good. Did it have an atmosphere? Noachian period. Sure did. Did it have liquid water on the surface? Because it had an atmosphere, the answer is sure did, right? Did it have a nice pressure that we probably would have felt comfortable? Sure did, right? This was actually the best time. Was it warm? Because of the greenhouse effect? Sure did, right? Had all of those great properties that would have made life possible on the surface of Mars. Does it have it now? No, right? So actually in a minute, I'll tell you that question, right? How does Mars become dry and cold, right? What were the stages of that development? Okay, so you don't need to know. I mean, I put them on there just because you could put them in order maybe. So which one came first? Noachian. Which one came next? Hesperian. Which one is it today? Amazonian. Okay, they're in order. Okay. All right, next question. Describe some of the features of Mercury's surface and why NASA announced 2 years ago now why it is still alive. Okay, we already mentioned that. What's the answer? Why is it still alive? New lobate scarps, new wrinkle ridges, right? Not a lot, just some, okay, which means that the core is still shrinking. Explain how Mercury can be seen to have a thin layer of hydrogen and helium, but not really an atmosphere. Why is that not considered an atmosphere? What is an atmosphere? Gases that are held to a planet by the force of, the only force that can hold things together. Come on. Gravity is not the only force, but it's the one that we're talking about, right? Atmospheres are held by gravity. So why would Mercury have a hard time holding on to gravity? Because it's very close to the sun, temperatures get really hot, and therefore the gas molecules are going to move really fast, and that means they can get away. So Mercury's small, close to the sun, no magnetic field, right? It's got a lot of problems. It can't have an atmosphere. Why would we see a little bit of hydrogen and helium near the surface of Mercury or near Mercury at all? Where did it come from? From the sun, from the solar wind. So the solar wind is made of hydrogen nuclei, helium nuclei, and electrons, and some of that gets stuck temporarily on near the surface of Mercury. And so while it's there, it kind of looks like atmosphere, but it's not. It's not atmosphere. So that's it. So it's just temporary from the solar wind. That would be my explanation. Okay. Next one. Describe some of the differences and similarities between the terrestrial planets. What are some similarities? All of them have cores, Made of iron and nickel, metal. Okay, but say iron and nickel because we know that actually, right? They're made of iron and nickel. Mostly iron, a little bit of nickel. There's more, but anyways, good enough. And do they all have the next layer? What's the next layer called? Mantle. Do they all have mantle? They all have mantle. Do they all have crust? They all have crust. There's some similarities. Great. They all have atmospheres too, right? Oh, that one doesn't work. Okay. Which ones do and which ones do not? Mercury? No. Venus? Lots. Earth? Pretty good. Mars? A little tiny bit. Okay, but still some. So we actually saw that little video where they try to land on Mars, right? They did land on Mars, and they mentioned the problem. The Martian atmosphere is thick enough that you have to worry about it, but not thick enough to slow you down much, right? So you have to use a giant parachute and all that crazy stuff, okay? So that's some similarity. What's the difference? Are all the planets alive? Is that true or no? So Mercury, Venus, Earth, Mars, are they all alive? Are they all changing at the surface in some way? The answer is yes. They are still all alive. Okay. And all right, we can talk about that. Do they, all right, so, okay, what are some differences? Are they all the same size? No. Who's small? Smallest. Mercury, smallest. How big? A little less than half the size of the Earth. How about Venus? How big is Venus? About the same size as the Earth. How big is Mars? A little bit more than half the size of the Earth, okay, but still pretty small. Okay, again, some of the things. Do they all have magnetic fields? Yes, no, maybe? Mercury? Yeah, fossil magnetism. Venus? Pretty much nothing. Why? Okay, why doesn't Mercury have magnetic field? Let's try to go through that methodically. Why? What would be your explanation? Does it rotate? Kind of, yeah, slowly, but it rotates, yeah. But what would be the reason why it doesn't have magnetic field? The core is solid because it's cooled off. It's a small body, right? No molten metal. That would be my explanation. How about Venus? Molten metal? Of course, Venus is molten metal. Therefore, it has a magnetic field, right? Unfortunately, no. But in Venus's case, why doesn't it have a magnetic field? Incredibly slow rotation in the wrong direction, right? Very, very slow rotation. Earth, magnetic field. Mars, no, because again, same story as Mercury. What was it? It's too small. It couldn't hold on to the heat energy. So what must have happened to the core? It's solidified. There's no molten metal. Okay? So no dynamo effect. Okay, so list the evidence which supports the, describe by Mercury. I just did that. Oops, I jumped to the next question. Why do Mercury and Venus and Mars do not have strong magnetic fields? Okay, we got that. So the Mercury and Mars, too small, so solid core. Venus, too slow, right? And list the evidence that supports the idea that Mars was once a wet world. What evidence do we have? We have lots of evidence now. I mentioned to you something last year we heard from NASA. That's pretty exciting. NASA announced what? Liquid water. Where? Underground lakes, right? And I also mentioned, I don't think it'll be on the test because this is highly controversial, but I do find it amazing, and I really want you to reflect on this. The simplest explanation is there is life right now on Mars, okay? And there is a biosignature, not necessarily, there is another way, but the simplest explanation for the methane gas, which is seasonal, right, would be that there's life on Mars. That's the simplest explanation. Now, NASA is being very careful, and they're saying, we have not said that. We did not say that. Okay, but I'm saying that because I don't care. I'm fine. Okay, I think I'm right. I think they found the first evidence of life on Mars. And so in a few years, we'll find out, right? It's whatever, I'm wrong, right? I'm wrong. But I think it's really exciting to know that there could be life. And then the next thing is to find it. And the next thing is to sequence it if it has DNA. And the next thing is to find out if we ever had a common origin, right? Oh man, the story is going to get so interesting. Okay. What if we find out it has DNA, right? And we have a common ancestor, right? What would you do? Man, what would that do? I don't know. I'm excited. I want to find out. Anyways, okay, we'll talk about that later. No, we won't. It's gone. Okay. Evidence. So we have that. How about, does Mars have any water left? It's pretty much gone. Lots of water underground, but in particular, a lot of it is frozen. I mean, it's not frozen. It's frozen. Sorry. No quotes. Frozen. Found where? At the poles. Okay. It's underground. And actually, speaking of that, we'll talk about, oh, it's coming up. It's coming up. Okay. So Mars has lots of frozen water. And we could be fine if we move there. We could find lots of water. It's polar water. Okay. About 80% of it's water, maybe. But we could talk also about the blueberries, hematite. We could talk about sedimentary rocks that we find at the surface. We could even talk about that big Mariner Valley. How did that form? And one of the ideas would be that it was wet somehow. All right. How does Mars have the largest volcano in the solar system? I kind of talked about it already. What would you say is the best explanation? Why did it get the biggest, tallest volcano? Hot spot. It had a hot spot, right? Did the plate move or stay in one place? Stayed in one place, right? So one place to generate a taller and taller volcano. But then what made it possible to make such a huge volcano? You want to say something like the crust. Thick or thin? It's a thick, strong crust that can support the weight of an incredibly big volcano. You could also think that if I put that on Earth, it would not be able to stay there. It would sink. Okay, it wouldn't work. How do we observe seasons on Mars? Can we see any seasons on Mars? Does Mars have seasons, first of all? Okay, why does Mars have seasons? The tilt, okay? It happens to be really close to the Earth, 25 degrees. And I don't think you have to memorize that necessarily, but the tilt is what makes it happen. Okay, Mars takes almost 2 years to go once around, okay. How does Mars, okay, how do we observe seasons? How do we see seasons on Mars? Anybody remember? It has ice caps. Are they always visible? No, they're visible in the, which season? In the winter season, right? And in the summer, they go away. But in the winter, you can see ice caps, right? What are they made of? Ice, of course. Is it water ice? No, mostly made of what? Carbon dioxide ice, okay? So it deposits carbon dioxide. Where did it come from? From the atmosphere, of course, right? And then what happens in the summer? It just sublimates back up into the atmosphere. So it's temporarily there, and then it goes away again. Describe sunset on Mars. Did I show you this? Oh my gosh, I think I forgot. Anybody know? What color is the sky on Mars? What color is the sky on Earth? Blue sky, right? Blue? Everybody agree? Blue? Why? Because the atmosphere scatters blue light, shorter wavelength light, more than any other color. What color is the sunset on Earth? Kind of red, orange, right? When the sun is low, the only color that can make it through the atmosphere is the long wavelength reddish light. Now, Martian sky does not look blue. Who knows the color of Martian sky? There's a reason why it looks this color when you look at it with a telescope. It is red. It's the red planet, right? What color is the sky on Mars? Red. So which color light is being scattered? The long wavelength red or the short wavelength violet and blue? Okay, the one that's being scattered is the one you see. So long wavelengths are getting scattered. What about the short one? They're not getting scattered. So when you watch the sunset on Mars, apparently you've never seen this because I never showed it to you. I forgot. Let's do that right now, right? What color would you predict? Is it going to be red? No, that gets scattered. So what's left? The short wavelength. So when you go to Mars one day, I want you to stand there with the person you love as the sun goes down. Watch that sunset. And it's going to be this beautiful blue sunset. It's going to be amazing, right? Sunset on Mars. Okay, for those of you at home, we got to watch sunset on Mars. Actually, how do we know this? Because we have rovers looking at the sunset every day. Sunset on Mars. Oh, look at that. Oh, they may be hyper. That's a little bit touched up maybe, but that's okay. Just get it, whatever. Might be a little touched up. But anyways, it's the right idea, right? The blue color we see is not getting scattered by the atmosphere. The atmosphere has larger particles in it that scatter longer wavelength light. And so that the sky looks red, but the sunsets look blue. Right? It's kind of the opposite of the Earth for a very similar reason. Okay, explain why all the terrestrial planets began with CO2. I think we kind of started with that. The answer would be, comes from volcanoes, right? Volcanic activity. What happened to Earth's CO2? It got locked into organic matter, which then became rock matter, okay? And then left behind the nitrogen and the oxygen. So we have what is called a secondary atmosphere. Other planets, we don't see that much, not as much. So Mars, that's interesting. Does that indicate Mars was never alive? I don't know. I don't think so. I think it's just, I don't know. Can't tell you anything. Okay, here we go. I don't know anything. I know nothing. I'm not sure. Number, the last one, the order of events which led to Mars becoming a dry, nearly dead world. Okay, so Mars, how did it begin? So we had this beautiful Noachian period. In the Hesperian period, we started to see something happen. The core began to cool off, right? And because of that, we began to lose the magnetic field. So now you don't have a protective magnetic field. What will happen? The solar wind, which was being deflected, is no longer deflected. It comes in and energizes the atmosphere and eventually blows it away, right? Solar wind, which was deflected by the magnetic field, now blows it away. Now what? Well, you don't have a lot of atmosphere. What happens to liquid water when there's not a lot of atmosphere? It evaporates, and then it gets blown away. Okay, so we become dry because all of that liquid can't stay in the form of a liquid when there's not enough pressure. And then you also lost most of your atmosphere. You lost your greenhouse effect, right? You only have a very thin atmosphere. And so it became cold as well. So that's pretty much it. It's not really that hard. It's the main problem was you lost your magnetic field because you cooled off. Why did you cool off so fast? You were little, okay? A little planet cools off pretty fast. All right, 5 stages of the evolution. Anybody, you want to just try and name them right now? First one, molten stuff, right? Stuff gets together, it's molten. What happens? Differentiation, okay? You try to radiate some of your energy, and then you, as you're doing this, you're cooling, right? And you form a crust. It's called cooling, but really crust formation is kind of what we're saying. After that, things can still hit your little body, right? Hit your surface. And in the process, they make holes. They're called craters. So this process is called cratering. If you get hit by really powerful things, really energetic events, you can crack open the crust and the mantle comes up and fills in any holes. We call that flooding or magma flooding, right? And then the final stage, if you have a blank, you can get this. If you have an atmosphere, you can get weathering. Okay, those are the 5 stages of terrestrial planet evolution. Okay, tilt of Venus, you're supposed to memorize. It is inverted, which makes it look like it's rotating backwards very, very slowly. So what was the timing again? You guys remember? 243-day rotation, I think. 225-day period for revolution. Tilt of Mars. Oh, I asked you to learn that. Oh, man. Okay, memorize. Okay, memorize. I lied. What's the angle? 25 degrees. What's the time it takes Mars to rotate one time? 24 hours and 30-some minutes. 37, I think, right now. Okay, 24 hours and 37 minutes. Okay, all right, we're done. Chapter 6, moving backwards. Ooh, lots of stuff. This is the Earth. Oh, man, the sections get longer. Okay, the Earth. Okay, we've got radioactive decay. What do we mean by radioactive decay? What does radioactive mean? Another way to say radioactive. Unstable. Let's say unstable. Not stable. That means the atom doesn't like to be in that configuration. It's a higher energy state. So what will happen? It'll find a lower energy state, a more stable way of being. And the way that it does that is by transforming into a new element. Also at that time, it'll release some form of radiation. There are 3 kinds of radiation: alpha, beta, gamma. Okay, I don't think you really need to know that, not yet. But do you guys remember the names? What's alpha? Alpha particle. Anybody have a helium nucleus? A helium nucleus. Very good. And beta, electron, or a positively charged one called positron. Okay, that will come up when we talk about stars. It will turn out to be, you have to know that. Okay, but at the moment it's kind of a little bit exotic. It's a positively charged antimatter particle with the same mass as an electron. So beta minus is an electron, ordinary. Beta plus is called a positron. And then gamma means gamma particle is another name for a photon, little particle of light. Okay, usually higher energy. So X-ray or gamma ray, right? That's actually why gamma really is a good name for it. Okay, half-life is the time it takes for about half of the material to decay. So it's a little bit confusing if you've never learned about half-life before, because sometimes people think it's the time for half of the material to go away. Well, it is, but then if you wait one more half-life, all the material is gone, but it doesn't work that way. It's half of whatever material is remaining, right? So half of the material remaining will decay in a time called the half-life. So the idea would be, if I tell you the half-life, or I tell you the half-life, let's say I tell you the half-life, okay? Imagine I have a material. I'm going to give you a nice, easy problem, okay? I have, I don't know, let's see how much. I have 16 kilograms of a material, some radioactive material, radioactive. And the half-life of this material is 1,000 years. Okay, 1,000 years. Okay? So in the beginning, here's my time, and here's the amount remaining of the radioactive material, right? So when I begin at 0 time, right, I have 16 kilograms. Okay? How much time do I have to wait before half of it goes away? I have to wait a half-life, right? So 1,000 years. How much will I have of the original material? I'll have 8 kilograms left. Now, what happened to the other 8 kilograms? Does it just disappear? And the answer is no, it turned into more stable form, something more stable. It's still there. There's over here the amount of stable material. How about that? And by the way, it might not be stable. It could be, this is also radioactive, but I'd take another class on that, okay? This is just not necessary. But amount of stable, let's say that that's stable. And so you have, oh, here you have none, but here you're going to have 8 kilos. The other 8 kilos. So you have a total of 16 kilos, right? If you wait how long? If you wait another 1,000 years, which is a total of 2,000 years, right? How much do you have? You've got 4 kilos left, right? You still have half. So you never get rid of all of it. You only get rid of half of whatever you have. And so how much is remaining? I'm sorry, how much has turned? How much has changed? And the answer is, well, half of this 8, 4, and so add that on. I have 12 kilos of the stable version, okay? So this is actually, you guys see this okay? At home? Nobody's even there. That's okay. Maybe people will watch it later, right? Okay. Maybe I'll watch myself later, you know, just for fun. Okay. How many years? 3,000 years, which is another 1,000 years. Another half-life has passed. How many kilograms will be left? We're going to be down to 2 kilos, exactly half of what you started with. It doesn't matter what you start with. The half-life will take you, half of it will decay in that time. The other half will stay as radioactive. And so now over here, this is 2, this is going to be 14. Okay. 4,000 years, how much will I have? I'll have 1 kilo. And at this rate, how long before I get down to 0? A very long time. Right? It's not going to be easy to get down to 0, right? I'm going to have to wait a long time. But every half-life, it goes down by half. So eventually, it's going to be very low. You won't have to go that far. I will give you a problem on half-life. Can you do this? Then you can handle the problem. It's not that hard. okay? But half-life is the time it takes for half of whatever you have that's radioactive to decay, and the other half will remain radioactive, okay? Okay, core. Where's the core of the Earth? In the center. What's special about the core of our Earth? Is it completely solid? No, we have an inner core that is completely solid, and then an outer core which is still molten. Why is the inner core solid? The Queen song again. Under pressure, right? Okay, it's under more pressure. Being on the inner part of the Earth is the greatest amount of pressure. So the mantle, what's the mantle? It's the layer of molten rock outside of the core, and finally get up to the lithosphere, which is the upper part of the mantle and includes the crust. The crust is just the crust, I guess. Lithosphere includes the upper part of the mantle and the crust. Basalt, did I put quartz? I mean, did I put granite? I don't think I put that. What's basalt? You know what basalt is? Basalt is dark, high density material, right? It's SiO2, silicon dioxide, but it's denser. It has some other stuff in it too. Basalt is typically dark, and it actually, if you think about solid magma, right? Take magma and solidify it, it becomes quickly, sorry, opposite. I'm not a geologist, I just messed up. Magma that cools quickly forms a very dense thing called basalt. Magma, which is given the opportunity to cool very, very slowly, grows crystals in it that cause the material to have a lower density, and we call it granite. So you've heard the words granite and basalt, and there's just differences, physical differences. Their densities are very different. So granite is a lower density silicate, and basalt is a higher density silicate. They're both made of the same stuff, right? Maybe a little difference in impurities or something. Anyway, so what's the crust made of? Well, those two types of materials, granite and basalt. So which type of crust is made of granite? The continent crust, right? Continental crust is made of granitic material, granite. Lower density. It always floats, right? Where do you find the basaltic materials? In the oceanic crust, right? Oceanic crust quickly forms because it forms where continents are separated, right? They're separating. The oceanic crust forms at a spreading center. And so little by little, right, the continents will separate and form oceanic crust. And it's denser, so it sags, which is where the oceans are gonna go, right? The places between the continents. Seismic waves, they come in two types, P waves, S waves. Why are they called P and S? Reason one, primary. Reason two, secondary, right? So P waves are primary wave, S waves are secondary waves. Why? Because one of them gets there first. So they both come from an earthquake, different ways of shaking. One is like this. That's the primary wave, right? It vibrates along the direction that the wave is propagating. And the other is going like this, right? Up and down as the wave is propagating. So that turns out to be a slower process. Secondary waves are also called shear wave. Heat transfer, we have conduction, convection, radiation. Where are any of these happening in the Earth? Okay, and the answer is yes. Which one? Okay, how about the answer? All of the above is the right answer. So where do you have conduction taking place? In particular, give me one place. There's at least two that I can think of. Actually, maybe three. I don't know. Well, give me one. Inner core to outer core, conduction, right? Solid touching something else, conduction. I think probably you could even say outer core to mantle is conduction too, right? That's the way that the heat gets transferred. So yeah, definitely, I would say that, conduction, okay? They're touching, and that's transferring heat energy to the lower part of the mantle. But the lower part of the mantle won't stay there. It moves, right? In these giant plumes called convective rolls, right? And that's actually what we think causes plate tectonics, right? So what is that? That's called convection. All right. And finally, the upper part of the mantle touches the crust. How does the heat energy get into the crust? By conduction again, right? Because it's touching, contact. And then the last one, does radiation happen? It happens when it gets away from the Earth, right? The way that heat energy escapes from the Earth is by radiation. That's the only mechanism. If you take a body and put it in space, the only way to get heat energy away is by radiation. That's it. Okay, so how do all planets cool? By radiation, ultimately. That's it. That's the only thing you got. And that's why Jupiter and Saturn are causing some interesting things in their environment, especially Saturn sublimating its rings, right? Saturn is sublimating its rings. Okay. A plume, what does that plume refer to? The magma upwelling, right? And we call it a plume, and it's moving really fast, right? Not really. How fast? Anybody remember? You don't have to know the numbers probably. 10 centimeters per year. It's really tiny. Okay, this far per year, right? This far. It's not very far. A shield volcano, a regular volcano, like the ones in Hawaii, right? And they're formed little by little, layer by layer. That's called a shield volcano. Plate tectonics, and in particular, there are 5 things you're supposed to know about plate tectonics, right? The 5 were continental collisions, right? What happens there? Continental collisions. You build up mountains, right? Give me an example. An example would be the Himalayas, the Himalaya mountains. An old example, former example, but now they've worn away from erosion. Which one? I mentioned to you in the eastern United States, the Appalachian Mountain Range, right? This was one of those too. Okay, it was a long time ago, and so they're not tall anymore. They've been worn away. Okay, how about subduction? Okay, one plate rides up and one plate rides down. Which one goes on top? Continental crust. What goes on the bottom? Oceanic crust. Why? Because oceanic crust is a greater density. It gets pulled down. Eventually, it will crack off and fall back into the Earth, right? Where is that happening? It happens right here on the western coast of South America. That's a subduction zone. There are more, but that's just one example. Okay, how about a hot spot? Hot spot, what do you think of? Hawaiian Islands. Did I mention Yellowstone? I didn't mention that. Yellowstone's another example. And actually, there's a trail of spots along North America, but you don't have to know. Let's do the Hawaii, okay? And maybe you remember also that they have changed direction, right? They weren't always moving like this. They have changed direction. Hot spot is a weaker spot in the crust where the magma can come up and form a volcano. But often, because the plate is moving, you don't get a single volcano. You get a chain of volcanoes, a volcanic chain, islands, chain. Okay, spreading center is where 2 crusts are moving away from each other. Originally, they were continental plate crusts, but now we can see this right here. The mid-Atlantic ridge is a spreading center. The plates are moving away. And what happens naturally when you leave a gap? The magma comes up and fills it. So the newest crust is right here. That's where you find it. That's an example. There are other examples off here. There's another one. But anyways, don't have to know that. Just that one example. And the last one, transform fault. What happens when the plates rub across each other? They transform next to each other. You get earthquakes, right? And so, for example, the San Andreas Fault is an example of that. And in fact, we are riding on the Pacific plate right now, Santa Barbara, okay? And next door, we have the North American plate. And when they get caught on each other, we can have an earthquake, right? That's something that can happen. Okay, now we're talking about the atmosphere, the layers of the atmosphere. The lowest layer is called the troposphere. What's happening in the troposphere? Pretty much everything, right? That's where all the weather is, where all the moisture is. The clouds are in that layer, right? That's mostly where they are. The weather is in that lowest layer. That's really where the water is, most of the water. A little bit higher, but not most of it is not. The stratosphere, the layer above the troposphere. Is there anything in the stratosphere that you need to know about? Ozone, that's an important one. The ozone layer is in the stratosphere. Is ozone good for anything? What does it do? Does it protect us at all? What does it block? Ultraviolet. Some of the ultraviolet photons from the sun are being blocked by the ozone layer. Above the ozone layer, we have the middle layer called the mesosphere, right? The mesosphere means little middle. And we saw in our picture in the slide set that there's streaks across that. Why? Because meteors flying through the atmosphere will leave a trail right there, okay? I feel like maybe I should mention something about that too, but all right. And then right above that, we've got the ionosphere. What's special about the ionosphere? It's electrical, right? It's got lots of charged particles, ions, right? And because of that, it's electrically active. We can bounce radio waves off of it. It's also an interesting part of the Earth. There's much more than we will talk about in this class. But anyways, it's electrically active. Okay, ozone, we just mentioned. Greenhouse effect. What's the greenhouse effect? Greenhouse effect, basic idea. Sunlight in the form of blank can make it through the atmosphere, but not in the form of blank. This is the greenhouse effect. Sunlight in the form of visible light can come right through the atmosphere. It's transparent to visible light. But once it's absorbed by the Earth, it's re-radiated in the form of infrared. And which layer of the Earth is blocking infrared? The bottom layer, troposphere, mostly water, but it turns out water is just one of the greenhouse gases, water, H2O. So mostly it's because of the water, but we also have a couple more greenhouse gases. What are they? CO2 and methane, right? Those two are definitely causing problems, okay? And in fact, as we heat up, the methane is becoming more of an issue because there are parts of the Earth that weren't producing methane that are now producing lots of methane. So that's actually accelerating the issue. But the key one for us as humans is we could control the amount of CO2 that we emit. And so given the option, please try to remember your Earth, okay? Take care of the Earth. Reduce greenhouse gases, okay? So little greenhouse gas is good or bad? It's probably the reason we are alive, okay? Without the greenhouse effect, we would be a snowball planet. So we like a little bit of greenhouse gas. The problem is too much of a good thing is not good anymore, right? When you melt your ice caps, it's an unstable environment. So the more heating our environment goes through, our atmosphere goes through, the more unstable it will become. So that's a big problem. All right, magnetosphere. What's the magnetosphere referred to? Any planet with a magnetosphere, the region where you have a magnetic field, okay? And so what's good about the magnetic field? It protects us from the solar wind, okay? Number one, we already heard that Mars lost its magnetic field and, as a result, lost its atmosphere. So would that happen to the Earth? Something similar would eventually happen to the Earth, okay? But don't worry about that. We have a long time before we need to worry about that. Magnetic dynamo effect, the dynamo effect, just call it dynamo effect, says what? How do you generate a magnetic field? With metals or something conductive, right? And something, it's electric currents inside of the body. The circulation of charged particles is what we call electricity. Electricity creates the magnetic field. So circulation of charged matter, electric currents, create a magnetic field, okay? That's called the dynamo effect. Okay, solar wind, what's the solar wind? Is it the light coming from the sun? No, that's called radiation. What is it? It's the particles. What kind of particles? Positive and negative particles, charged particles coming from the sun. They're like little tiny bullets, right? They are hydrogen nuclei, aka protons. Maybe some neutrons too, so that's not charged. But anyways, mostly protons, mostly helium nucleus. So, mostly protons. Next would be helium nuclei and electrons. Actually, electrons probably goes first. Never mind. Mostly electrons, if I had to weigh them. Then come protons, then come helium nuclei. Okay, that would be the order. You don't need to know that, but just lots of them. Okay, and it's constant, although it does have periods when there's more or less. And we're going to talk about that in chapter 10, which is coming up after the test, okay? Aurora Borealis, and there's another one called Aurora Australis, right? What does Aurora Borealis mean? Aurora in the north, Aurora Australis, Aurora in the south, northern lights, southern lights, right? Why do they occur? The solar wind hits the magnetic field of the Earth. right? These charged particles cannot go straight anymore, and they spiral around the magnetic field. And as they do, they give off their energy to the atmosphere of the Earth. The atmosphere begins to glow. Okay, it's not the particles, it's the atmosphere of the Earth that is glowing, right? It's getting energized by the charged particles' energy. And so we have them in the north and the south. Where are they the strongest? At the poles, right? Where they're the weakest, at the equator, right? Strongest at the poles. Tides, right? We have high tide, we have low tide. Why do we have tide? The moon, right? But also because of the sun and the moon. Which one's more important, sun or moon? The moon is more important, twice as important. You want to remember that, right? The moon is the one that tells you when you have a high tide and a low tide, okay? When the moon is right above your head, do you have a high tide or low tide? You have a high tide, right? The moon is saying, hey, high tide, come towards me, right? High tide, high tide. And also on the far side of the Earth, you have a high tide. But if you go 90 degrees away on the Earth, you have a low tide, right? The water has to come from somewhere. And so you have two high tides, two low tides per day. It's a 24-hour day. About how many hours between high tide and low tide? About 6 hours, right? How many hours between high tide and the next high tide? About 12 hours, right? About. It's not perfect, and that's okay. Don't worry about it. We're not doing that. But the sun is also important, and therefore, you want to remember that there's two special kinds of tides. One where the tides are super big, super high highs, super low lows, really big extremes. And the reason is because both the sun and the moon are pulling on the Earth in the same direction. And this happens at what two phases of the moon? New moon and full moon. New moon and full moon. That's what you got to remember. In those cases, the sun and the moon are stretching the Earth along the same direction. And so you get what is called the spring tides. Okay, it's right there. Oh, by the way, what is tidal force? What is tidal force definition? The difference in the force of gravity between the near side and the far side of a body. And it acts to stretch the body out. Tidal force. Keep that in mind. We need to learn this later when we talk about black holes, which is next chapter. Okay, next test. Black holes. You guys are learning black holes coming up. Oh, it's so exciting. Good stuff. Really fun. Okay, I know, a lot of stuff. So spring tide, when they're lining up, when one of them pulls here perpendicular, and one of them pulls like this, they work against each other. Right? So if the moon is pulling here, do you have a high tide here or a low tide here? You got a high tide. The sun is over here. Does it stop, change it? No, it's still high tide here. But by pulling over here, where the low tide should be, the sun is going to pull the low tide up, so you're going to get a high low tide. And over here, which you're supposed to get a high tide, because you pulled material away from it, you're going to get a low high tide. So you get a little tiny variation in the tides. And that's what we call a neap tide, right? So spring tide, really big changes. Neap tide, not so much. Okay, little tiny subtle changes. Tidal locking, we've mentioned it before, right? In which case, what situation we have tidal locking? The moon going around the Earth. One face faces the central body. And why did it happen? Because of tidal forces. And so what does it mean? It means your rotation period matches your revolution period. They have to be the same. And then you'll get tidal locking. What's a crater? A hole in the ground. How did it get there? Impact event, right? Something hit the ground. So where do we see craters? On the moon. Lots and lots of craters. But not just craters. We do have areas called maria, or mare for singular. And they looked originally like seas. That's why they were called mare, right? They look like oceans. In fact, they are what color? Very dark, low albedo, made of basalt, right? In fact, they're examples of which stage of terrestrial planet formation? Anybody remember the name? Magma flooding, right? So what happened on the moon is they got hit really hard. We think there was a period called the late heavy bombardment, right? About 4 billion years ago. And in that late heavy bombardment, the moon was actually hit particularly hard on certain parts, and the magma just came out of the inside, out of the mantle, and flooded in any valleys that were present on the moon. So they became these beautiful dark basaltic plains. Are there any craters there? Yes, but only a few. The other areas that are not dark are called the highlands, and they are higher, and they are actually light colored, and there's craters everywhere. So which one is older, the highlands or the lowlands? The ones with lots of craters, highlands, is much older than the lower parts with no craters or almost no craters. Okay, they're called the Maria, late heavy bombardment. I mentioned that. Giant impact hypothesis, what are we talking about? That is the most likely scenario for the formation of the moon, right? We think that the moon got hit by a Mars-sized planet, protoplanet, I guess protoplanet, and then launched material into orbit, which then eventually coalesced to form the moon. There were a couple of other competing theories, but we've ruled them out. One was called the capture theory, and that one, the moon would be extremely different composition, but it's not. It just doesn't work. And then the other is called the daughter or the fission hypothesis, where the Earth was spinning so rapidly that a big chunk of material flew off, or a bunch of material flew off and then coalesced to form the moon. In that case, it would be just like the surface of the Earth, but it's not. Okay, so we really like the giant impact hypothesis. Questions? Are you good? All right. Determine the amount of substance. I did that with you already. Okay. Determine how plate tectonics lead to different formations. I think I did that too. One more time. Continental collisions form new mountains. Subduction form new mountains as well, but not quite as tall, right? So the Andes mountain range is not nearly as tall as the Himalayas. How about spreading center? What do you got? New oceanic crust, right? How about a hotspot? Volcanoes, right? And a transform fault. What do you get? Earthquakes, right? Okay, you don't get necessarily, you can get some interesting things, but mainly shaking of the Earth. Okay. Let's see. Describe the structure of the Earth atmosphere. I think I did that as well, right? We got the layers. What are they called and what's special? I think I covered that. You guys okay? The layers are called troposphere, weather, all the water. Next one, stratosphere, ozone layer. Mesosphere, not sure what to tell you except the meteors go through there, leave streaks. Top one, ionosphere, electrically charged. Okay. How does the greenhouse effect work? What gas? What type of light comes through the atmosphere? Visible. What doesn't get through? Infrared. Okay. That's the greenhouse effect. How does the magnetic field function? It deflects the solar wind, and some of it gets trapped and forms the northern and southern lights. Okay, aurora borealis, aurora australis. Describe, compare the relative strength of the sun and the moon on Earth. Okay, so actually this is supposed to be, I think I might have told you, right? A lot of people get confused. They think, hey, the moon makes the stronger tides. That's true. Which one pulls stronger on the Earth, the sun or the moon? And the answer is the sun is much stronger. That's why we go around the sun, right? I mean, if you think about it, that's kind of obvious. The force of gravity on the Earth is much stronger from the sun. But the tidal force from the moon is twice as strong as the tidal force from the sun. So the tides are mostly from the moon, a little part from the sun. But the fact is we go around the sun. The Earth and the moon go together around the sun. Okay, explain why the capture and fission theory do not fit observed data. Which model is accepted? I think I did that, right? What's the right model? Giant impact hypothesis, okay. How did features on the moon form? What are the features? The mare? How did they form? So, yeah, bombarding, crack open the crust, flooding, right? The magma coming up from inside fills in any valleys. How about the craters? Well, things hit the ground, ejecta form. Okay, it's pretty obvious. All right. But when you see lots of craters, we know the surface is old. Actually, even more, it's kind of cool when you look at craters on the moon. Some of them are sharp and it clearly circles, and some of them look kind of like ragged. And what do you infer from that? Well, the raggedy ones have been around a while, and every other crater that happened nearby helped to erase it a little bit. So the ones that are fresh look beautiful, perfect circles. The older ones start to look not so great, okay? Orders of the layers and their approximate size, I didn't do that. I don't think you have to know that. But you need to know the lunar period is 27.3 days. That's the time it takes to make one revolution around the Earth, also called the sidereal period. It is also the time it takes to make one rotation. Okay, one rotation. Okay, we do have one final section. Can we just jump to that? You can leave if you need to leave, because we're almost at a 2-hour period, but I think I'm going to be done in about 15 minutes. Okay. Oh, man, there's a lot. Maybe not. Okay. You guys want to keep going? Yes, no, maybe? Raise your hand. I do not want to keep going. I'm done. Okay, you just leave. I'll keep going. Why not? I'll stay. All right, I'll be here. I'll just do it for nobody. I'll do it for you. I'll do it for everybody here. So you're not nobody. You guys are here. Okay, but you leave if you got to leave. You got to go. See you later. You can go. You don't have to stay. Don't feel obligated. You already know this. It's good. You got it. Okay, Kuiper Belt object. An object found in the Kuiper Belt. Where's the Kuiper Belt? Outside, out past the orbit of Neptune, you want to say, right? Outside the orbit of Neptune. So that'd be 30 AUs from the sun and out, right? Outside the Kuiper Belt, you do have another area, a donut shape called the scattered disk. Outside the scattered disk, you have a very big sphere called the Oort cloud. Okay, those are kind of the structures you have to know. All right, exoplanet. What's an exoplanet? A planet around another star, not our star, another star, exoplanet. Dwarf planet, example, Pluto, right? And we learned that there are 3 rules for being a planet, or 3 things. It was established by the IAU in 2006, okay? We'll learn a little bit more about this after the test, okay? But in 2006, they said, rule number 1, a planet has to go around the sun. Does Pluto go around the sun? Yes. Okay, number 2, a planet has to be spherical. And why would it be spherical? Because what force makes it in a sphere? Force of gravity. You've got to be a big enough mass that you pull yourself into the shape of a sphere. Is Pluto a sphere? Yes. 2 for 2, right? And number 3, the one that it fails, right? A planet has to sweep out the region of its orbital path of debris, right? It has to get rid of any debris that's in the orbital path. And because Pluto goes into the Kuiper Belt and has not swept out that area, we say, you're not a planet, Pluto. You are called a dwarf planet. So a planet that follows at least the first 2, but fails on the 3rd one, the reason is because you have to have a big enough gravitational force to disturb or influence things that you go in the neighborhood of. And Pluto's just not big enough, okay? Or anybody that big, it's just not going to be big enough to pull in objects, okay? Kuiper Belt, asteroid belt. Sorry about that one. Asteroid belt. What is the asteroid? Yeah, question. One more time. Sorry, Pluto. Yes. Oh gosh, that's a really great question. Actually, the question was, does Pluto still have collisions? Do things still hit Pluto? And the answer is definitely. And oh man, you don't need to know this, but they've been actually trying to study the sizes of craters on Pluto in order to figure out the size of objects in the Kuiper Belt. So if you look at the sizes of craters, you can work backwards to try to estimate the size of the object that made that crater. And in this way, try to come up with a statistical model of what the objects in the Kuiper Belt look like. We don't really know, how many big things there are and medium-sized things and small things, but we're trying to figure that out. And the way we do that is by looking at the craters on Pluto. So the answer is everything is still getting hit. Everything, every planet, everybody is still getting hit, right? So we're not done with our evolution of our solar system yet. Not at all, right? We're still getting hit. The major things have happened already, right? Any planetary migrations that were going to happen happened already. Unless an outside visitor comes by, we're done evolving in a major way as a planetary system, as a solar system, right? Now, if a big object comes through or a star comes through, will that mangle some of the orbits of our planets? Perhaps, right? It could, but you need an outside force to cause changes, right? There has to be an exchange of energy and or momentum. Otherwise, nothing's going to happen, right? So we're in a pretty stable configuration right now. Okay, I don't know why we're talking about this. You don't need this. This is too advanced. Okay, moving on. Scattered disk, we mentioned. Oort cloud, we mentioned. Terrestrial planet, where do you find them? What are they? Solid, found closer to the star, terrestrial planet, right? Actually, in our solar system, they are the 4 innermost planets, right? Names are Mercury, Venus, Earth, Mars. Made mostly of iron, nickel, and silicate rock. Okay, that's what they're made of. Okay, the gas giants are made of mostly, where are they found? First of all, a little further out, right, past the ice line. Gas giants are Jupiter and Saturn, mostly made of hydrogen and helium, like the sun. Okay, and then the furthest ones out, Uranus and Neptune, are called the ice giants. They are also have some hydrogen and helium, but they have lots and lots of ices, and they have a little cores. Okay, they are much smaller than the 2 other gas giants. Uncompressed density is the idea of the total mass divided by the total volume. And what we found out today, we talked about it, is that the planets that are close to the sun have much higher densities. The planets that are further from the sun have much lower densities. Which planet has the lowest overall density? Saturn, right? It's kind of funny. Less than the density of water. All the others are greater, and definitely the terrestrial planets are much greater. Planetesimal, what's a planetesimal? A small body that would have been present in the early solar system and that looks a lot like an asteroid. In fact, an asteroid is probably the perfect example of a planetesimal, or a Kuiper Belt object, right? Asteroid, Kuiper Belt object, these are examples of planetesimal. Is it a planet? No, it's a piece of something, right? If you get enough of them together, then you will form something called a protoplanet. Again, is that a planet? Not yet, but it's something that has the potential to grow into a planet, because now a protoplanet has enough mass that it can start to use gravity to pull in other matter. Okay. Now, in the very beginning, how did the planetesimals form? It wasn't from gravity. It was from collisions. Now, the very beginning, by the way, was just a bunch of dust. How did the dust get together to form smaller clumps? And that's coming up. The answer is static electricity. It's the only force that would really allow little tiny particles to stick together. They had positive and negative charge. They attracted each other. Okay? That was the very beginning. Then they would bump into each other, not too fast, right? Just a nice slow bump, and they could merge together. And as they grew, you would finally get these things called planetesimals, right? So they were kind of like the early pieces that may or may not have gotten together to form planets. In one part of our solar system, they did not get together to form planets. Where was that? Actually, 2 places. The asteroid belt and the Kuiper Belt are 2 places where planetesimals did not get together to form planets. Everywhere else, they did. Okay, Trojan asteroids, those are special, right? Those are found, actually every planet has them, but they were first discovered near the planet Jupiter. We mentioned them in class today. They're found at 2 of the Lagrange points, L4 and L5. They're found 60 degrees ahead and 60 degrees behind Jupiter in its same orbital radius, okay? And Lagrange points, there are 5 of them. They are special mathematical places where the gravity of the sun and the planet work together to make special kind of situations. And so an object can orbit in these Lagrange points, even though it shouldn't be able to. And it's through the combination of the sun and the planet's gravitational force. Earth-crossing asteroids, the name tells you what it is, an asteroid which crosses the path of the Earth. But this means it could potentially one day hit the Earth. I mean, that's the reason why we're caring about it, right? Differentiation refers to when large collisions happen, right? Bodies get together, they heat up, and because they're molten, they can separate by density. We call that differentiation. Now, did that happen in the asteroid belt? Yes, it did. Sorry, we got to remember it did. Okay, so did protoplanets maybe form in the asteroid belt? Yeah, they did actually. Most of them did not, and they are called C-type asteroids. C-type asteroids are carbonaceous, which means they never got together with anybody. They are raw material from the very early solar system. But the other 2 types, S-type and M-type, are interesting did get together. They were a part of a larger body. So that larger body must have gathered together material, heated up, and because it was molten, which layer went to the middle? The metallic layer went to the middle, and the stony layer was on the outside. But then it smashed into something or got broken apart. And what happened is some of the material went off and became M-type, and some of it became S-type. We have families of asteroids which were generated in this way. So the M-type asteroids came from where? From the core. They are metal type. And the S-type came from the mantle of this big protoplanet. And they would have been stony. They're the stony type meteor asteroids. Okay, Snowline, the place where we talked about the crystallization that occurred. Right, it's called the condensation sequence, and the type of dust that you had very close to the star was metal and metal oxide. A little further, silicates. Further out, the ice line or snow line, about 4.5 AU. It's the only one we wrote down a number for. Is where you get water ice, right? And then further away, like Kuiper Belt kind of distance, you get all the, actually not even that far, but you get Uranus maybe. Uranus is better actually. Uranus distance. You get other types of ices. Methane ice, ammonia ice, nitrogen ice, oxygen ice, okay? Albedo, we've mentioned that word a number of times today. The ability to reflect light. High albedo, you look very bright. Low albedo, you look very dark. Okay, light and dark. So dark colored surface has a low albedo. A bright colored surface, or the rings of Saturn that are bright and reflective, have a high albedo. Okay, comet nucleus. What are we talking about? The core of the comet, right? And then around that comet nucleus, you can get something called the coma. Now, do comets always have a coma? And the answer is no. The coma forms when the comet is coming closer to the sun. The heat of the sun causes what process to occur? The solid turns directly into a gas. It's called sublimation. And then you have a coma. So here's the way it might be heard on a test, right? If a comet is near aphelion, that's a word that you should know. Aphelion means what? Furthest from the sun in its orbit, furthest from the sun. Does it have a coma or not? No, no coma. No coma at all, right? As it starts to approach the sun, it's getting hotter, right? And the coma begins to form, right? So at some point, you will start to see it, right? The comet appears as a fuzzy star because of this coma, right? So it starts to get brighter as well as a result of that. And when it's near perihelion, it has the largest coma, right? The largest coma would be near perihelion. Okay, the ion tail and the dust tail, there's two tails for the comet. And one of them is made of ions. That would be the ion tail. And one of them is made of fragments of comet, little dust, and that's the dust tail. One of them is straight. Which one is straight? The ion tail. And which way does it point? In the direction of the ions from the sun, called the solar wind, right? So the solar wind shines, or doesn't shine. What's the word? Is emitted by the sun. I don't know. Shines, not shining, right? It's projected. I don't know. Blows. There we go. Blow. I don't know. It comes out of the sun. Okay, it goes away from the sun in every direction. When the comet sees that solar wind, the ion tail will go directly away from the sun in the direction of the solar wind. But the dust tail remembers a little bit where it was because it's neutral. It's not affected as much. And so it has a little curve to it. Okay, so if you see a picture, the one that's really straight is called the ion tail. The one that's a little curved has a dust tail. Also reflects more light. Okay, short period and long period comet. You're supposed to remember that short periods have a period of less than 200 years. Anything less than 200, short period comet. And where does it come from? From the Kuiper Belt. A long period comet is more than 200 years, but really can be millions of years. And it comes from maybe as far away as the Oort cloud. Okay, it could be scattered disk too. We didn't say that, but that's true. Rosetta mission was a mission from which company? Not NSA, but not NSA, and never from the NSA. NASA, not from NASA, but from the ESA, right? The European Space Administration. And it was going to this comet, Churyumov-Gerasimenko, otherwise called 67P. And that was a really cool thing. It had a little, it carried with it a lander called Philae. And that's not on there, but it's on later in the quiz, later in the study guide. And so they went there and they stayed with it from the time when it was pretty far from the sun all the way past perihelion and back out again. And then they crashed it into the surface of the comet. Okay, so it's gone. But they learned a huge amount. They learned that comets are really interesting. Okay, and there's more to the story, obviously, to learn. But we did learn one thing: is the water on that comet the same water as the water on Earth? It's not. So the water on Earth did not come from that kind of a comet. Maybe from a different comet, although it looks like it's much more similar to the water on asteroids. So maybe not from comets. Okay, a bunch of words. Meteoroid. What's a meteoroid? These are just words. An object which could potentially fall through the atmosphere of the Earth. Meteoroid. A meteor, an object in the process of flying through the atmosphere. What does it look like? It's called a shooting star. It's shiny, it's light, it leaves a streak. Sometimes they're really big. They leave a big trail of debris behind them. A bolide is something that blows up as it's flying through the atmosphere. That was the example I gave you with the, what was it? Chelyabinsk, the Chelyabinsk meteorite. It exploded over the city and all the windows shattered and everything. That was a bolide. A meteor shower is a little bit different. This is a random thing. A meteor is kind of a random thing mostly, but a meteor shower is not random. It happens at the same time every year. Why do we have meteor showers? Because the Earth is passing through the trail of debris left by a comet, and it happens twice per year. Well, it can happen twice. The same comet can leave two trails, right? And when we go through either one, we get a meteor shower. But they happen at the same time every year. Interstellar gas. What's interstellar mean? Between the stars, right? And so we know that stars form from this stuff between the stars, and somehow our sun formed from this material. That's actually going to be something we talk about. Concept of center of mass was pretty important. Actually, I feel like maybe I should just take a second to remind you. I better remember how that works. We had two big examples that you need to know. If two objects have the same mass or if they have different mass. That's it, basically. They're either the same or they're different. Okay, if they're the same, where is the center of mass located? And if they're different, where is the center of mass located? Okay, you will have questions on your tests that are based on this idea. Okay, so center of mass. Suppose I had two equally massive objects. You have to. There's no math here, so it's just an idea. If you have two objects, and each one has the same mass, same mass. Where's the location mathematically of each one? And the answer is right at the center. But if I ask you, where's the center of mass for the combination, for the set, then the way you do it is you draw a line between their centers, and you think, right? If they're the same mass, mathematically, where is the center of mass? Right at the center. So there's nothing there, but that's actually mathematically where the center of mass is located. And so if I say to you that these two objects are orbiting each other, what I really mean to say is that they are orbiting the common center of mass. So that's the center of mass. And that means that the radius for this orbit will match the radius of this orbit. They'll have the same radius, okay? So in the case where the masses are the same, the radii are the same, they will always take the same amount of time to do their orbit. They have to, or they won't be in that nice configuration anymore. They're dancing around each other. So that means that the speeds of the two objects will be the same in their orbit. One will go up, one will go down, okay? Now, if we're on the Earth right here, right, we will look at them, and if these were stars, they would be emitting light. Even if they're planets, they would be reflecting light. But anyway, let's say they're stars, right? They'd be emitting light. If the star is coming towards you, what happens to the star light? It gets shifted by the effect called the Doppler shift, Doppler effect. And what kind of a shift will it be? Coming towards you is called a blue shift, right? This is a blue shift. And the one that's moving away from you? Redshift. Okay? So if they're the same, what can you say about the amount of the shift? Same velocity, same shift. But one is red, one is blue, right? They have the same speeds. Now, the more interesting problem, the one that you have to know, is what if the masses are different, right? So it's not a big difference, but a little, let's say this is a star and this is a planet, right? What happens as a result of having different masses? Well, one of the masses is big and the other is small. Small. Okay? So where is the center of mass? And this time, when you draw the line between them, you have to recognize that the center of mass is not in the middle anymore. Where is it? It's really close to the big one. In fact, if this were the Earth and the sun, the center of mass would be inside of the sun, right? That's actually how big the sun is compared to the Earth. With Jupiter, it's just outside, but either way, let's put it just outside, something like that. So as a result, they orbit a common center of mass. They take the same amount of time to go around, but the big mass will have a little orbit, The small mass will have a much bigger orbit. They take the same amount of time. So because one goes a lot greater distance, what can you say about the speeds? The small one goes much faster because it has to cover a lot more ground in the same amount of time. So this one is moving just with a little velocity, right? A little velocity, but this one's got to have a much greater velocity. So if we're over here on Earth watching them, if we look at the star, what kind of shift would we see coming towards us? Blue shift, but a big one or a little one? This is a small blue shift, right? And over here, it's a red shift, but a large red shift because of the greater speed. It's a large red, I think it's red shift. Why am I putting blue? Red shift, I don't know. Red shift, blue shift. I must be tired. I can't figure out. It's supposed to be one word or two. Blue shift, red shift. I don't know. I'm tired. You guys tired? Tired. Just want to take the test already. You ready? Sorry. Let's get through it. We're almost done. Okay. All right. So center of mass. Okay, here we go. So there are 3 techniques for finding exoplanets, right? One of them is not very good, one of them is medium good, and one of them is awesome, right? Incredibly good. So you remember the 3? So what's the one that's not very good? Ooh, it's not there. Oops. Okay. Maybe because it's not very good. Anybody know the not very good method for detecting an exoplanet? Taking a picture of it, right? Direct imaging of that exoplanet. Really difficult. There's 20, right? That's not very many. There are quite a few more using the next method. This is a medium quality method called the radial velocity method. And that's just what we see right here, the red shift, blue shift. That's the radial velocity method. But one of the things we talked about is, by the way, I'll just mention, what happens when a star feels the influence of a planet is it doesn't, in its orbit right here around the center of mass, we see it as wobbling, right? So the size of the wobble is determined by the exoplanet, right? So which kind of planets will make stars wobble a lot? And the answer is big mass or little mass? Big mass, right? And also close or far from the star? The closer they are, the greater the force, so what would you expect? The larger the effect will be, right? So a big, massive planet close to its star will have the biggest effect. So this particular method is really good at detecting large mass planets that are very close to their star. We call them hot Jupiters. See hot Jupiter up there on the list. So this method is really good at finding hot Jupiters, not so good at finding Earths, right? Not. So the third method, the one that is the best, the one that Kepler Space Telescope has used to find 5,000 planets, 3,700 whatever confirmed, 2,200 more candidates. I mean, this is amazing, right? In the last 15 years, we have completely changed our understanding of exoplanets. 2000, actually less than that, the last 10 years. So the Kepler Space Telescope used the transit method. The transit method involves a planet passing in front of its star. And when it does, the light curve has a little dip. So that's called the transit method. Mentioned transit method, Kepler Space. So super Earth is a Earth kind of a little bit like two times the mass of the Earth, 3 times maybe, similar size. Don't worry too much about that. Habitable zone, you need to know that one because I told you the story. So anyways, what is the Goldilocks zone or habitable zone? The place where an exoplanet could have liquid water at its surface, right? So you have to be not too close to the star, not too far from the star, just right. And then you get liquid water at the surface. Okay, hot Jupiter we mentioned. Conservation of angular momentum. Wow, we got that one, right? It's the idea that if you take a big ball of gas, really big, like a light year across, and it has a little tiny swirl, what has to happen when you collapse it? It has to go faster, right? That's conservation of angular momentum. And it has to flatten into the shape of a disk, right? That has to happen. You can get a picture of an early solar system that way. Condensation theory, we mentioned it a couple times already, but let me just remind you, it says that the raw stuff of a planet is dependent on where it forms in the solar system. So what kind of dust can form very close to the star? Metal oxide, but it can actually form anywhere in the solar system, including very close, right? And then a little bit further away, you begin to see silicate dust, and then anywhere further out, silicate dust. 4.5 AU in our solar system, we got water ice, and anywhere further out. And then finally, we got the other kinds of ices, and again, all the way out. Okay, so the further away you get, different kind of dust. Condensation theory was that when the sun, I just did that, sorry, protoplanetary disk. In the middle of the disk, you have the protostar. It is hot. It is shining with light. Is it a star yet? And the answer is no. It's called a protostar. It has not ignited. The reason it's hot is because of the conversion of gravitational potential energy falling together into thermal energy, kinetic thermal energy. Okay, interstellar dust grain, whatever. I don't know what that is. Never mind. It's just the raw material that the star formed. Core accretion model says that in order for a planet like Jupiter and Saturn to form, you had to first make a core that could then gather together hydrogen and helium. Alrighty, and our final little things here. Determine the period of the comet where it came from. We just mentioned short period, long period, right? The time is 200 years. Short period, less than 200 years, came from the Kuiper Belt. Greater than 200 years, we're going to say it came from the Oort cloud, but it actually could be scattered disk, but anyways, don't worry about that. Identify the ion and dust tail. If I show you a picture, which one's going to be really straight? The ion tail. Which way is it pointed? Directly away from the sun, in the direction that the solar wind is blowing. Comet, the dust tail could be a little curvy. Okay, so if you notice a little curve, it's brighter. It's probably the dust tail. Explain using condensation theory. Can I just skip that? You got that idea? All right. Describe how the principle of conservation of angular momentum is applied to solar system formation, as well as the movement of planets in the solar system. So I referred to the first part, right? When you condense, collapse, it has to rotate faster and flatten into a disk. But what happens if two planets interact, right? And in the early solar system, we think that some of the planets were born in different places and migrated, moved to another place. Can one planet move all by itself? And the answer is no way, right? How does it happen? There's an interaction. There's an exchange of energy and momentum. So if one planet comes closer to the sun, did it gain or lose energy? Anybody remember? If it starts orbiting closer to the sun, it lost energy. That means another body had to go further from the sun and gain that energy. You can't destroy energy. Same thing with angular momentum. Okay, it's an exchange that happens that causes a migration. Estimate the location of the center of mass. I just did that with you. And mainly there's two types, either the same or different. The different is the more interesting one. Okay, explain the activity of a comet. Where's the comet have a tail? Always? See you later. Bye. Tomorrow morning. Okay, where's the comet of a tail going to be the best? Close to the sun or far from the sun? Closer to the sun, the best tail, right? The further away you go, the weaker the tail becomes until it just disappears. Oh, I know what I didn't do this. Oh, man. I'm going to do this tomorrow morning for sure. But since you're here, when a meteor comes through the atmosphere, it leaves behind a trail, sometimes of debris, smoke, but definitely the light that we see. What is that from? What is the light coming from? It's kind of similar to the auroras. It's not the meteor necessarily. Often it's not. In fact, especially if they're really tiny, a little tiny grain of dust, a grain of sand, grain of dust, grain of sand, sorry, sand, a little bit bigger than dust, okay? A grain of sand leaves a streak that you can see, right? It's so much energy, right? It's the speed, the velocity most important, but mass and velocity both contribute. And the streak that you see is not the material of the stuff. It's the atmosphere glowing, right? It's the air, the atmosphere that's glowing. So the energy is coming from that object, but it's being given to the atmosphere. The atmosphere is heating up and starting to glow with that heat. So the very interesting question is, why does it get so hot? So you saw, for example, with the Mars rover landing, the shield gets really hot, right? Why does it get so hot? And the same answer applies in both cases. Why do things get hot when they fly through the atmosphere? Who knows the answer? So up until I started teaching this class a number of years ago, I thought the answer was friction. And that's just a tiny piece, it turns out. It's wrong. The real answer is called compressional heating. So when you take a gas and you compress it, it gets hot. And what happens to a meteor when it slams through the atmosphere? It compresses a lot of gas. And as whatever gas is getting compressed, it's leaving heat energy and heating up that meteor or object that's compressing it. So whether it's the shield of a spacecraft, a meteor, anything that's going to squish the air molecules together is going to get heat energy from those air molecules. So the larger it is, the more heat energy it's going to get. Okay, that's the reason that it heats up. Okay, so sometimes they blow up and they leave their own, they're actually using, okay, blah, 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 blah. M-type, S-type, where'd they come from? A protoplanet smashed together that it must have been large enough to differentiate. And then the inner parts became M-type, and the outer layer became S-type. M-type, metal type, S-type, silicate type. Hey, describe how the different methods of exoplanet detection work. Direct imaging, okay. Weakest, you got to take a picture and watch it change. Radial velocity, which is the Doppler effect. That one's okay, not great, but okay. And the best one is the transit method. Okay, that one is the one we have thousands of examples. Okay, explain why the recent discovery of 7 habitable planets around TRAPPIST-1 is so exciting. 3 of those planets were in the habitable, 3 or 4? 3 are in the habitable zone. So it means that we can find planets now that are Earth-like, perhaps, right? We don't know that for sure because we haven't seen the signature of water, but they could have liquid water at their surface. And that's one of the requirements we think for life. So you're looking for places that could have life. There you go. There are some places. The asteroid Ryugu, I didn't tell you the name, but this is the Hayabusa. This is the Japanese JAXA, Space Administration. And they just took samples, right, from the asteroid. It's a sample return mission. I don't actually think I asked any questions. I just think it's cool. So, and I was ready to ask you a question, but I had too many questions. I had to cut questions. So that's the way it goes. But there you go, you know it. Okay, keep going, memorize the locations of the planets. The order of the planets are Mercury, Venus, Earth, Mars, asteroid belt, right? Jupiter, Saturn, Uranus, Neptune, Kuiper belt, scattered disk, Oort cloud. Okay, that's our solar system. And the Lagrange position, do you want me to draw the whole thing? Did I do it? I do 1, 2, 3, 4, 5 in class. I did it in class today. I think that's good enough. All right, thank you guys very much for your attention. You're going to do great tomorrow, I hope. And if you come tomorrow with any questions before we take the test, you can ask your questions. Okay? Thank you. All right, home. Goodbye. Nobody's here, but anyways, maybe. Oh no, 2 people came. Hey, 2 people. How you doing? Okay. And